everybody? Welcome to Coffee Hour with Paul. My name is obviously Paul, and thanks for taking time out of your day to join us for Coffee Hour to get your week started, get your day started. It's Monday, it's the beginning of the week. Hope everybody had a great weekend. As you know, I had been out of town. It was not vacation, I was out of town. I was in McKinney at our corporate office for Encore Wire and Prismium, working on some training and some products in all this kind of good stuff in the wiring cable industry. And excited to bring some videos in the future that will expand on their product line. Most people know that Prismium and Encore Wire now are one company, and they are massive, and they offer cords out the wazoo. We're talking about the flexible cords, extension cords. That's the lower end side. The other stuff, they got this stuff called Clearview. It just a crazy amount of corded products, many of which are also dual listed to be permanently wired, whether you knew that or not. And there's so many other applications, SJ, SOO, SOW, just crazy amounts of cords. Obviously electronics, we call them electronics, but it's really the data center cables, the coaxial cables, the Cat 5s, Cat 6s, the alarms. Anyway, tons of stuff. Plus, of course, all of the normal stuff we have, tray cable, medium voltage products called AirGuard. Crazy stuff that we'll be bringing and showing you in future episodes, and possibly even having interviews from people at the company so you can learn a little bit more about the products. It's an incredible collection of products, and again, it's just amazing stuff. So we'll be talking about that. But that's what I was out. I was working, wasn't on vacation, was out working and trying to see where I could be a fit to help, with the products and talking codes and standards and all that kind of other good stuff. That's where I was at. So it's a great time traveling out to McKinney. Y'all know I lived there for about 11 years, and it's a great little town. I say little town. I shouldn't say that. It's a great city. It's over 250,000 people there now. So it's a big city, much bigger than where I'm at here. Yeah, I hope everybody had a great week and watched the replays and got a little something out of the replays. It's always important to watch something over and over again. And again, it solidifies things. A couple announcements this morning to make it clear. Some of the things I told you when I got away, it also allows me to think, and it allows me to refocus on things that we want to do for the show. And I realized that, and I talked to Jeff while I was gone, I realized that we lack getting everything. We're still not at a rapid pace of getting everything moved over to Fast Tracks Tube from YouTube and all those others. Things get in the way, and I have so many things that we're doing that we don't get it moved properly. So we have to refocus on movement and get everything. Also, as far as merchandise, I made a decision, and it was supported by the board, is that we're going to be removing a lot of the products that we have in our merch stores, like the mugs and all this kind of stuff. Not that we don't sell quite a bit of them. It's just that we don't make the margins that's worth us doing those products. In other words, I'll give you an example. We sold a travel mug the other day. And we made $1.25 on the mug. Now, you might say, well, Paul, if you're selling a bunch of stuff, $1.25, it doesn't make the margins. And like any company, you're electrical contractors. We have to make sure we meet certain margins. And when the price of the products, due to whether it's imports or whatever it is, drives the cost up to where margins, and we're not going to change the price to the consumer. Some people say, well, why don't you just jack the price up? Then it creates that albatross type of thing, whereas that product is grossly overpriced, in our opinion, based on what you could go buy somewhere, even if it's customized. So we're going to be drastically dropping things from our merch store. What we're not going to drop is our engraved products, because we can control the price of those, and we can keep them as low as possible. So minimalist wallets, the coins, the coasters, you saw some of the new coasters that we have, these type of things. All of these type of etched stuff, we're going to keep because we have those in-house. We can control these costs. What we can't control is the third party stuff, the print on demand stuff that have our custom designs put on the products. We really can't control that. Like I said, when you're making like selling a $35 product and you're making $1, it's not worth the effort because we still have to support that product. If you get it, you don't like it, we are the ones that have to support it, and we really have no control over the change. So we're going to be dropping those things. Obviously, we're an electrical education company, and our main focus is to produce training videos, and all that type of stuff. So we have to refocus that type of stuff. So I'll be weeding all that out as well. Also in the trade hog, we will, I believe we're going to be going away from monthly subscriptions to annuals. Right now there's offered both. So if you get in now, you can choose what you want, annual or monthly. But we are slowly going to be going away from the monthly because, again, we have enough people that say they just don't like the monthly reoccurring thing. Same that we did in Fast Tracks 2 for our videos. It's just an annual. So we hear you. And I, again, am not a fan of monthly reoccurring type of charges. I just don't like to see it. Whether I use something or not, I want a one-time, I pay it, and then I just do it annually. And it's not big on the monthly thing. So we'll be making a change to that too here shortly. But again, there's still merch there. There's still the monthly Fast Tracks, the Trade Hug. Take advantage of it now if you want, but we're going to be tuning those things back here in the next couple of days. Okay, next, the drawing for Q2. It looks like it's going to be the end of this week, either Thursday or Friday. Right? We'll have the show. We'll announce it on here, but it looks like Jeff has everything. We have everything ready to do that. We just have to get it all set up. So we're going to do that. Again, drawing out of the hat, that type of good stuff, and pulling people's names. And you'll have a unique email address that you'll be able to send your information to. So that way it's going to be really quicker than what it was before. As always, I live vicariously through you, folks, and I do have an inspirational story to share with you today. We are going to be talking transformer disconnecting means today, purely the disconnecting means. We're not going to be talking about the conductor protection for primary and secondary, although when you talk about transformer disconnecting means and you start talking about Article 450, you realize really quickly that when you're sizing the protection for the transformer, that you may also be sizing the protection for the primary conductors or the secondary conductors, okay? And there are rare occasions where you don't have to have protection on the secondary because they're protected by the primary, okay, that type of thing. So that's a unique situation where it's a single voltage on the secondary and the primary, like a 480 to 240. It's not 240, 120. It's just one voltage on the secondary. Same if it was just 120 on the secondary. Then there are applications in 240.21C1, which means that the primary would also serve double duty. Protection would also protect the secondary and those type of things. So not really as deep as we're going to go in today's episode, but we have talked about that before in other episodes as well as videos over on Fast Tracks 2. Okay, but we are going to talk transformer disconnecting mean protection because I got a request by somebody that didn't understand transformer protection and where it had to be located and what had to be done. So again, as I always tell you, if you want a topic to be talked about, the easiest way to do it is to send something to me here at paulabernathy.com. Just go to paulabernathy.com and fill it out and send it in and ask for a request. That's what this was done. Somebody asked me for transformer disconnecting mean requirements. So I figured I would talk about that today. Okay. All right. So as always, do me a favor. Let me know who you are, where you're from in the comments. And we'll go through those pretty quickly and see if we can see who all's here. What's up? Good morning, Frank. Glad to have you in the house. Jonathan's in the house. Good morning. Glad to have you here, my friend. Adam is in the house. Adam, good morning again. It was not really a time off. I was working. I just didn't have the internet connections while traveling to be able to offer any type of morning show. But I was kind of working every day, reviewing products and codes and standards and all that kind of good stuff. What's up, Crypto? Glad to have you here. Welcome to the show. David, our CMECP's in the house. David down in Florida, glad to have you here, my friend. Everybody's throwing in that hashtag win. We have another CMECP in the house. Okay, Jason, welcome. Glad to have you here, my friend. Sporting the CMECP logo. That's what I'm talking about. What's up, Paul? Glad to have you here. I am glad to be back into the studio, back into the office, back in whatever anybody wants to call it. I had somebody laugh and send me something, said, Paul, why do you call it a studio when it's basically a room in your house? Well, yeah, it is. And it's dedicated just to recordings. And the other room is dedicated just to podcasts. But it is a studio because that's all I do in here. Okay. So so I'm like, it's amazing how people concern themselves with other people's activities. But hey, whatever floats your boat. Okay. So where my server is. This is where all my equipment is. Everything is right here. Let's see here. Good morning, Paul. What did he say? Oh, sorry about that, Paul. Ran out. You're back from vacation, ready to get back into learning. Well, we're glad to have you here, my friend. Welcome. David Bueno, good morning. Glad to have you here, my friend. Everybody's throwing out that hashtag. Glad to have it. There we go. There is Manny Sanchez. All over on Facebook. So Facebook's working. We know that's working. Thank you. Glad to have you here. Let's see here. What do we got? We got CMECP. Another CMECP. The room is full of CMECPs, so y'all be good because there's people here that are checking you. Good. Thomas, working up at the airport again, right up the road. All right. Let's see here. Hope I had a good time in Texas. It was great seeing everybody at Encore. People, all, family. I lived with, basically family for the last 11 years working in Texas. So it was great. We spent most of the time just head down to the grindstone and working on codes and standards applications and where we need to do. And we determined that they want me to do more videos for them, which y'all might like, getting very specific into products because I think when you have a company that has so many products, and it's not I'm not a sales guy. Y'all know that. I will not push a product. But there's so many applications that people just have no idea what type of product they need. And since Prismium and Encore are the world's largest manufacturer of wire and cable, there's nobody close. They're an $18 billion company. They make intercontinental cables. They make medium voltage, high voltage. They make transmission lines, utility lines. They make cords, electronics. They make a little bit of everything. And of course, the building wire aspects as well, which picks up the Encore wire piece. Tray cable, all kinds of stuff. But many people struggle with the application. Where could I use this? Where would I use that? So we're hopefully going to do more of that videos for them. And of course, they'll be available on the internet, I'm sure. They won't necessarily all be available on my channel because this is for Prismium and Encore. But hopefully we'll be able to identify out a lot of products and really people get confused. And one of the biggest areas of confusion is cords. When can you use a cord for this or that? Or DLO. People don't understand DLO, which is not in the NEC. And there's a such thing as a listed application and a non-listed. You have a DLO by itself is flexible, but it's not listed. Then you have what's called a DLO RHH RHW-2 type of product, which is not listed for DLO, but it does pick up dual ratings for RHH. So you can get the benefits of flexibility and ignore the DLO, but really get the benefits of a DLO. Anyway, a lot of stuff. Hopefully we'll do videos in the future on that. They asked me to do that, and I most certainly will do that. In order they have an advantage is that I can probably break down that product. Those products is better than probably most anybody when it comes to wire and cable. So we'll see. Let's see. Angel, I am doing great, my friend. Glad to have you here joining us. Red Dog is in the house.
Woo, 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 woo. Big dog.
Good morning. Glad to have you here. The jig is ready. So I will be reaching out to you, trying to see what you want on those collector plates, that type of thing. So good. We got that all set up. It came in. Darlene got it down here, and it looks good. It's just a jig. So I'm doing good. What's up, Angel? Glad to have you here. You sold Throwing up the hashtag win. If you want to get into Q3 spin, and on the Q3 spin, we have added the coasters, these type of things. They're just neat little coasters. I use them, as you can see behind the scenes, can see that I'm using a coaster right now for my Diet Pepsi. There you go. Let's see here. Marlon, good morning. Glad to have you here. Pedro, good morning. Glad to have you here. Manny, what's up? Good to have you here. Hoodies and t-shirts, I believe all of that stuff will be going away, Manny. So if you've got something, you got to wear it. Now, anybody that's got a pending order, I've been traveling. I'm sorry, it's behind. We'll get you taken care of this week. Promise you, everything that's anybody's ordered will be shipped out this week. It's been a little delay on that. I apologize. But yeah, we will probably be getting rid. You have a rarity there. We'll probably be getting rid of most of our hoodies and t-shirts and all that because I don't, the margins are not there, and it's just I hate relying on other people and third parties to make our products like that. Is just scary for me now. So I mean, you got something nice, so other people are getting good stuff, but it's just not enough margins for us to keep supporting it. You'll understand. What's up, Pedro? Out working, driving, drive safely. What's up, Peter? Good morning. Glad to have you here. What is up, Christopher? Glad to have you here this morning. Trying to get through these names. Santana's doing the hashtag win, trying to get some morning goodies. What's up, Terrence? Glad to have you here. Okay, welcome. Eddie's in the house, doing the hashtag win as well. Good morning, Eddie. Work hard at it. There you go. Let's see, what else do we got here? Francis, good morning from Jersey. Good morning, Francis. Glad to have you here. Adrian, good morning from Houston. Glad to have you here. Mike from the outdoors. There you go. Good morning. Glad to have you here, my friend. Let's see here. What else do we got here? James is in Mississippi. There you go. Paul, I have an idea. Why don't you make bookmarks for the code? Use formulas, tables, like the Uglies book. I want one. It will sell. We have looked at doing things like that, but not too deep with it. Bookmarks. The problem is I don't know how well things. We're not trying to get rich on merch, but again, I don't know. We don't have that. Y'all know I'm not about the clicks, and so we don't have something like Dustin has 500, 600, 800,000 exposure, and so you sell products that way. We don't get a following like that. I mean, if I have collectively 100,000 across all platforms, they tend to not be really consumer driven. I mean, they don't buy a lot of products that we have, and we have a lot of products. We don't sell a lot of that merch. It's spotty what we sell. So I don't know if they will or not, but it's not off the table as long as we can control it, right? If we can control it, then we may do it. But if we have to have a third party do it, then we're just trying to get away from third parties. We want to be able to ship everything out of here. I don't like when third parties, that type of thing, I just can't control them. So I can't control the quality and things like that. So we'll see. What's up, Robert? Glad to have you here, my friend. Let's see. William, good morning. Glad to have you here. David A., good morning. Okay. Let's see. Terrence says, Paul, Internet still uses your advanced legal training videos. Yep. They do. And I haven't done any updates to it in years. They haven't reached out to me to update it in training. And it's like anything. When you do some training for somebody and they pay you, they own it. So it's theirs. So, yep. Internachi still uses my training. What's up, Rob? Glad to have you here. Let's see. Good morning, AJ. And Selmo, good morning. Glad to have you here. Skyattle or Skiattle or Seattle. Seattle. You haven't told me how it's properly pronounced. I'll say it all kinds of ways. What's up, Greg? Glad to have you here, Greg. Good morning from Ohio. Poppy's in the house. Whoop, whoop, big dog.
Woo, 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 woo. Big dog.
In the house. It's going. Samantha, good to see you here. Leroy, good morning. Good to see you here. Samantha's throwing out the hashtag wire waffle this morning. Van Man's in the house. Good morning. Glad to have you here. Getting a jog in. Samantha, staying healthy. There you go. That's what I'm talking about. I need people behind the scenes over on TikTok. By the way, behind the scenes stream on TikTok are looking. They're probably thinking Paul needs to do a little jogging because they can see Paul's gut from behind the scenes. All right, let's go over and get into talk about some lessons today. Again, as always, folks, I live vicariously through you. Let me know who you are, where you're from in the comments. If I see it, I will give a shout out. And also, by the way, for those that do not know, do me a favor, make sure you check out Fast Track's Tube. There's videos over there that you won't see on YouTube. And I think it's most certainly, if you want to invest in us and help us, it's worth the $99 annual subscription to see those exclusive videos. Okay. So appreciate everybody that subscribes to Fast Track's Tube. All right. So let's talk about it. We're going to talk about transformer disconnecting means today. Let's turn off this banner so I can make sure that I see all of you, all of your comments, that type of thing. So we're going to be talking transformer disconnecting means. And remember, what we're talking about is the protection for the transformer. Now, it may or may not provide adequate protection for the conductor's primary side, that type of thing, or even secondary side. So we have to consciously think about that when we're protecting the transformer, right? Is whether or not, because it would do us no good if we have a transformer's primary protection, right? And we're going to be talking disconnecting means today, though, first. But talking about overcurrent protection, it does us no good to protect the transformers on the primary side if it doesn't also protect the primary conductors, and in many cases, even the secondary conductors. So all those things are extremely important when you're dealing with transformers. Now, I know most of you out there probably 99.9% of you probably don't even look at this stuff and that's why we're going to talk about the disconnecting means, because that's what can vary in the field. As far as protection of the transformer and conductors, y'all probably don't look at that much, probably because the engineers do that for you, right? If you're doing, unless you're doing an as-built or you're doing these projects where you're just putting transformers in the field, or you're adding something after the fact, adding an additional transformer or something like that, then you probably don't deal with an engineer. But if you do deal with a design professional, they're probably going to already calculate this out. They're going to have looked at the load calcs that's going to be served from that transformer. Size that transformer might be oversized so they can have expansion. That transformer might be supplying multiple panels, right, on the load side, which is perfectly okay. You can have multiple secondary conductors as long as you don't exceed the rating of the transformer, right? So you could have secondary. It doesn't just have one transformer feeds one panel, right? So again, people get confused with that. They serve multiple panels if it's sized properly, that type of thing. So anyway, all this is typically done from an engineer. So where the electricians get involved is like, okay, based on something that the engineer wasn't aware of, a wall gets added or its location changes a little bit or something, then all of a sudden you're dealing with, okay, now I have to add a disconnecting means. Now, if the disconnecting means is placed in a location, then I have to make sure it meets accessibility requirements and all those type of things. So it can leave it up to the electrician to determine, okay, well, what are the rules for a disconnect and when it comes to a transformer? So that's kind of what we're going to be looking at today. And then if we've got time, we'll dabble into some protection. I will remind you that we do have multiple videos over on Fast Track's Tube on transformers. You just go to the search feature and type in transformer or transformers with an S, and you'll see videos that are germane to that topic. So again, use the search feature over on Fast Track's Tube. That's why we put it there. And that's why we use keywords in order to be able to help you navigate and look for certain things, okay? Especially as we add new videos. Okay. All right. Transformer disconnecting means. Good morning, Green Tech Electric. Good morning. Glad to have you here. All right. Now, we're talking about transformers. So transformers other than, okay, so we're talking general transformers, power transformers like you probably deal with every day, other than the class 2 or class 3 transformers, okay, which are smaller typically. If you think of what's a class 2 or class 3 transformer typically is found in a lot of equipment where it's going to have the load side or the secondary side of that transformer is going to be running a very limited power source to a limited load. Whereas class 2 is essentially the same thing, but one of the good examples of like a class 2 would be something like a transformer for a doorbell transformer or something like that. But just remember that class 2 and class 3 typically have limited output than you would have with a traditional power type transformer. Okay, that type of thing. Or even a class 1 type transformer is basically going to have a voltage range and everything, and output is going to be higher than a class 2 or class 3. So class 2, class 3, think smaller, think limited output, things like that. That's the easiest way to try to differentiate it. So first of all, we're talking transformers. And when's the last time you saw a secondary or any disconnect for a class 2? Okay, or for example, like a doorbell. When you usually have the breaker for a branch circuit, it's applied doorbell transformer. You have primary side connection, which is 120, and then the output could be 24 volts, could be 12 volts, could whatever, okay, based on the transformer. And that's typically what you see. So we're talking transformers other than those that have limited voltage output, limited current output. That's what we're talking about, right? It says those regular transformers like you and I deal with every day. Well, I don't deal with them every day. You deal with them every day. Shall have a disconnecting means located either in sight from the transformer. Okay, so that's the first one. So if I'm going to do a power transformer, it could be a 480, 240, primary 480, secondary 240, or it could be a primary 480, secondary 240, 120. It could be a primary 480 and a secondary 208, 120. Depending on the type transformer you have, I have to have a disconnect either within sight. So on the primary side, I need to be able to shut that transformer down, isolate it, or I can do it remotely. And that means if there's maybe not enough space at the transformer, maybe the transformer is lifted up higher, right? The 25 kVA or less, maybe it's above a suspended ceiling because they can be on a certain kVA. So maybe it doesn't behoove us to put a disconnect there. Maybe I won't meet clearances. Maybe I got other issues, space limitations, things like that. Well, the code doesn't allow me to do a remote disconnecting means for this transformer. Okay, now that was there. It says or in a remote location. So we'll just do that in a different color. Now, when doing so, it says we're located in a remote location. Okay, it says the disconnecting means shall be lockable in accordance with 110.25. Okay, so what does that mean? That means you got to meet all of the rules, lockable, okay, and all of those requirements in 110.25 have to be met, okay? And there's one other element that's involved. If I'm going to do a remote, so my disconnect is not beside my transformer, primary side, if it's not beside my transformer and it's remote in an equipment upstream somewhere, then I have to make sure that I do the labeling requirement. What's the labeling requirement? It's going to require me to put a label at the actual transformer to let me know where that disconnecting means is located, okay? And that's all covered in 450.14. So as always, you folks see these chevrons, right? We have chevrons, and in our Fast Tracks program, for those that aren't in our Fast Tracks program, the URL is up there in the logo. For those that aren't in that program, the reason we do these chevrons, okay, is so that you will actually go and look at the requirements, okay? So we're going to do it by the magic of code here and the magic of technology. We're right here. So here is 450.14. There's the disconnecting mean. And again, other than class 2 or class 3 transformers, okay? It says shall have a disconnecting means located either in sight of the transformer or in a remote location. We're located in a remote location. The disconnection means shall be lockable open. Okay, so lockable open in accordance with 110.25, and its location shall be field marked on the transformer. Okay, so that's the rules, and there's really no additional commentary here. So let's go down and look at the lesson, and this is what we're talking about right here. Okay, so this is the graphic we're talking about, and I can blow this up a little bit for you, maybe a little bit. There we go, just enough. So here's an example where you've got your disconnecting means for the transformer. Okay, all right, and here this means is lockable. Okay, so it's got some kind of mechanism on here that once you in the open position, you can put a lock on it. Okay, so nobody can inadvertently come and switch that sucker on. It's the last thing you want. And so here, maybe the engineer didn't know that wherever they designed it, there just wasn't enough room. Now, this looks like there's probably enough room to put one. But anyway, the choice was to not put the disconnecting means here. Okay, so if that's the case, this is your primary. And here's the label that's required. Okay, it says transformer disconnecting located in switchboard LJM. You can see this says LJM here. You probably can't see that, but it's right there. Okay, and it says in the electrical room. Okay, now if there's multiple electrical rooms, then maybe I'd be a little more specific. Electrical room E2, whatever it may be, because it needs to give the accurate location of where the disconnecting means happens to be located. In this case right here, this disconnecting mean right here, okay? And this says the disconnecting means for transformer CRM. This is all part of the legend labeling requirement that has to be very descriptive on what that overcurrent protected device, which in this case is also the disconnecting means, is controlling, okay? So again, this is covered in a directory labeling requirement. This label here on the transformer is literally covered by the rules in 450.114 saying, look, needs to be field marked, telling you where is the location of the disconnect for this transformer. Okay, so that's what it's kind of locating. All right, so we covered that's the basics for that aspect of it. So let's go on now. So now let's kind of look in, for all of you that are familiar with our callouts, we're going to talk about this disconnecting means a little bit when, where you have one, things like that. So here first, since the transformer's disconnecting mean is within sight of the transformer, it's not required to be field marked the location of the transformer. So what is this? That's this one right here. So obviously this disconnect, it's amazing enough, we're going to assume it is supplied through the back inside the wall because it doesn't show anything coming in from the left or anything like that. So we'll assume it's coming out the back. It's coming out the back. You know it is. So in this scenario here, this right here, there's no reason to have any markings. Okay? No reason to have any markings. Okay. Now, in this case right here, one of the questions I get from people, if this is like an FMC right here, chances are the sizes of this are larger and this FMC is not to be used as any type of equipment bonding jumper or anything like that. There's no overcurrent protection device here. So typically your supply side bonding jumper would be either in here or it's permitted to be in here. Typically not both because now we have a metallic path between them, right? So again, it's either here or here, okay? Either way. But you're required to have it running through here is going to be basically an equipment bonding jumper or supply side bonding jumper. It's on the supply side of this panel here. This is not service though. This is feeder. Obviously, it's the secondary conductors from a transformer. But in here, if the supply side bonding jumper is in here, right? Then over here we have a system bonding jumper is in here, by the way, excuse me, system bonding jumper. Then a supply side bonding jumper is run out here, and then you separate the grounds and neutrals in this panel, right? That type of thing. Now, one of the questions that people do ask is if I run a supply side bonding jumper through here and terminate it on the equipment bus, do I have to run it through a lug here and bond it to this enclosure? All right. So one of the things you have to think about, is it over 250 volts to ground? So we'd have to think about the rules in 250.97 and all those rules up there. But in this case, typically on a transformer, the holes are punched, right? So there's no concentric or eccentric KOs. So typically In this scenario, the bonding part of it is all taken care of based on the FMC into a listed fitting that has a shoulder on it that mounts against the actual transformer. And so typically on the inside, you're going to use your lock nut or whatnot, that type of scenario. And you're not going to need to have a separate loop it through like a bonding lug because, again, the bonding takes place with the fitting onto the actual armor itself. So that's some allowances. Again, when you're not dealing with any concentric or eccentric or any impairment here, if I was dealing with an application of over 250 volts to ground on the secondary, that type of thing. Okay, so right here of this transformer. Okay, whole nother story, whole nother grounding and bonding episode. We do have videos for that over on Fast Tracks Tube that talks about the grounding and bonding when it comes to transformers and secondaries and things like that. Now, if you want to bring your supply side bonding jumper and you want to loop it through a lay-in lug on there, go for it. It's totally up to you. It's not a big deal. You can do it if you want. Okay, it's just not required if you're punching your own holes. Okay, and kind of also think about that as the same kind of rule as the feeder application, right? A feeder application, standard fittings, all those type of things work fine. You get what I'm saying? So it's one of those things that you have to think about, okay? So one of the, David says sometimes he sees a green wire on it. So bonding jumper applications, there are some allowances as long as it's not more than 6 feet. There are some to maintain integrity, okay? That type of scenario. But remember, in most of the transformer applications in this panel, if the system bonding jumper is installed in here, okay, then what we're running through here is going to be 4 conductors, let's say, or it may even be more than that if you've got A, B, and C, and then you have a neutral, and then you have the supply side bonding jumper, which may also run here, okay, in this scenario. Okay. One of the things to remember that you could also have a solid raceway here, not likely, but you could have an EMT or something like that, and then you wouldn't have to pull a wire through here, a wire type supply side bonding jumper, because you could use the raceway if it is non-flexible. I do not see that ever. I don't. It's very rare for me to ever see anybody run pure something like an EMT over to it. Okay, usually it's a small section or something like that. Okay, but remember the supply side bonding jumper is different. Okay, it is different than maintaining bonding requirements on something like an FMC. Okay, and doing a bonding of this product. Okay, scenario. Now, most people say, well, I'm going to get away with it by just simply doing a lay-in lug or lay-in lug on each side and laying it through, and then they don't really have to do anything here because it don't have to run a bonding jumper outside because the bonding assured for this is taking place. Okay, so again, totally depends on your installation. We'll talk about that maybe in an upcoming episode because I can see where that could be confusing for folks. So we'll look at it. I think we'll look at some images here in a second. But let's finish these off real quick because we're not really talking about the grounding and bonding scheme today. We're really focused on the disconnecting means. So let all of our collective ADH or AHD or what, attention deficit disorder, let's all of us refocus back on the topic here and not get into grounding and bonding. Let's talk about transformer disconnecting means. Okay, so this one, obviously, no labeling required. It's right next to it. This one, remote, obviously, labeling requirements, right? Let's see here. Let's look at some other call-outs. Let's see, B. What's up, Ryan? Good morning. Tara, good morning. I see you in here. Anthony, I see you. All right, let's see here. All right, so let's see. Each disconnecting means shall be legibly marked to indicate its purpose unless located and arranged so the purpose is evidence. We just talked about that, and that is your 110.22a. The markings, sufficient durability, means you're not going to be using ink jets. You're not going to be using just a peel and stick because these get hot, and that label could just fall right off. you know, this label. Hold on. This label right here. Okay, so typically this is like something phenolic or something that is going to be able to handle the heat, handle the environment that it's exposed to. All those type of things are covered in 110.22. So I'll be honest with you, I have been to a lot of panels that have that phenolic, you know, the plastic where it's etched in it. And the glue on that stuff is so freaking strong that inside, not an issue. Outside, they can fade because it is plastic. It can fade and that type of scenario. But on the inside, very common to use the plastic phenolic type of engraved type of plastic panels in order to do identification. See those all the time. I would not allow a simple inkjet because, again, as it gets hot, it'll cause that paper to dry out and it'll just start to peel right off. That's not going to be permanent. Just my thoughts on that. All right, let's see what else we got here. So, okay. So C, if the disconnect mean is required to be in a lockable open elsewhere in this code, it shall be capable of being locked in the open position. The provisions for locking shall remain in place with or without the lock installed. So it has to be inherent to it or something installed so that even if the lock is not there, it's still in place. We do this in a panel. When we do this for a panel is the kind that snap into the actual cover or snap onto the breaker so that it's in place in whether or not the lock is put there or not. So that's some of the rules in 110.25 for that type of thing. Let's see, and yep, so we covered most of everything. So that's our disconnect first. So that's our disconnect requirements. So if you're installing a transformer and it's just the disconnect transfer, it's just the disconnecting means, that's all, okay? Then you have to make sure that it is installed either within sight of the transformer, or if it's remote, then it has to have the labeling and all that. Now, remember, we're talking disconnecting means for with transformers, hardly never would it be just a disconnect. It's going to also either have fuses in it, circuit breakers in it, whatever that's also going to be providing the protection to the transformer. Okay? I wouldn't waste my money putting a disconnect, right, and that type of thing, and not provide the adequate protection to the transformer or even what's necessary for the conductors. Seems like I would be adding stuff that's just a waste of money. Okay, so just keep that in mind. This case right here, I am sure there are fuses in there. Right, so it is a disconnect, but it's also probably sized for the primary protection for the primary conductors, but it's also the disconnect, and it probably also provides the 450.3 protection for the transformer, all in there. But remember, we're just talking disconnect at this point. That's all we were really talking about, that function, if you will. Okay. Let's see here. Okay, so the number one transformer thing that we all talk about is protection for the transformer. We'll talk about it, the primary protection. I think in most all cases, not all cases, because you could have some that are less than 9 amps. Very small application, very specific driven. Probably as an electrician, it's not what you're going to deal with every day. You're probably dealing with transformers every day that are 150 amp, 125s, 225s, that type of thing. Okay? Yep. So, Anthony. Anthony says, nope, Paul, we're talking about disconnects. Yeah. Well, we already covered pretty much all we can cover on the disconnect part. So we got to move on to protection now of the transformer. All right. So when it talks about protection of that transformer, we'll kind of look at something. So conductors supplied by the secondary side of a single-phase transformer having a 2-wire secondary, okay, or a 3-phase delta-delta connection transformer having a 3-wire, and both of these are single voltage, okay, secondary, can be protected by the overcurrent protection situated on the primary side of the transformer. Okay, let me explain this part real quick for those that are confused by that. So there are unique applications where I can have a transformer and the primary protection for that transformer, okay, that primary protection can not only protect the transformer, okay, but it also can protect the secondary side of that transformer, provided the type of system that it is. So if it's supplying that transformer and you're supplying it with a single phase or three phase, and we're dealing with a single voltage. Okay, so example of a three phase may be if I'm coming in 480 and I'm coming out with a 208 or something like that. Then if that's one single or it's coming out with a 240. So if I'm doing it's delta delta. So we'll go 480 primary and 240 secondary, and that's it. Not a 240 120. It's a delta delta. Okay, three phase delta delta. It's just one single voltage coming in, one single voltage going out. Then there is a situation, and we have to do the math, but there is a situation where that primary that's protecting the primary of the transformer can also protect the secondary. Okay, so that's an application where it's specific to one single voltage on the primary and the secondary. Okay, and a single phase application may be a hold on, I'm gonna lose everybody on TikTok. A single volt may be that is a 240 volt primary and simply a 120 volt secondary. Okay, that type of scenario. Okay, so that is the scenario that we're dealing with in that type of situation. Okay, all right. So if that's the case, if we're dealing with that, okay, dealing with it, Anthony, I don't know what you're rattling on about. Okay, so I have no idea what your motivation is. I'm not sure what you're talking about. All right, so this is just a allowance. So let's get into what normally we would see. Okay, here's what we would normally see for transfer. Let's go if we got an image here. Okay, so here is so it's 9 amps or more. This is your typical installation that we may see here, where you have a primary overcurrent protection, and whether or not secondary overcurrent protection is required or not. One thing to remember, though, is even in a situation where we're going to look at the tables, right, that secondary protection may not be required. Okay, secondary protection of the transformer may not be required. However, if this is supplying a panel board, then we have to remember there are rules in 408.36 and things like that that require us to protect that panel board. So where you may think, okay, for the transformer's purposes, you may think, well, the code's going to say I have protection on the primary, but I'm not required to protect that transformer on the secondary, okay, because of maybe what size it is or what the table tells you. But then if you happen to be supplying a panel board, then you have to worry about the protection of that panel board. So then it will require some type of overcurrent device to be in that panel board because you have to protect the panel board, that type of scenario. Okay, so that's the kind of things that we're gonna look at. All right, so let's do some call outs real quick and see what we got. All right, A seems to be calling out this primary side. Okay, so A says where 125% of this current does not correspond to the standard fuse or non-adjustable circuit breaker. Okay, just a normal circuit breaker. Inverse time is example of a non-adjustable circuit breaker. It says the next higher rating described in 240.6 is permitted. And this is all given to us in table 450.3b1. So what I want to do is I want to go look at that table real quick and show you kind of what all it's talking about. Get me that real quick here. Okay, so first things first, what we're talking about right now is overcurrent protection to protect the transformer. That's it. We're not talking about the conductors, right? Okay. I'm not sure what you're going into, Anthony. I'm trying to talk about overcurrent protection. If you got questions, feel free to send them to paulabernathy.com if you want to make this your show, that type of thing. I'm not sure. All right, so let's talk about here. So A, what are we talking about? So let's go down. Here's the transformers over. So we're going to be talking transformers, 1,000 volts nominal or less, okay? type of scenario. Here's the code. Samantha, what's the code call out? Wow, y'all are strange today. That's the call out. 450.3b. That's what we're talking about in the first thing, dealing with this 125% protection for the transformer. Okay? First thing. That's why we're here. All right, so where are we at? All right? So here we're at the ratings. So let's pull this table up. For what piece of the table you can actually see. So this is what it's talking about. So if it was primary only protection, means that all we had was primary only protection, right? So this is what we're talking about down here. If this is primary only protection, right, then I can go up to 125%. So in order to determine this transformer, as you know, we need the kVA. We have the kVA divided by whatever the primary voltage is, right? And that's going to determine our amps, right? So that is our amps for that transformer. Then we take it and we can take that at 125%. Now, what we're saying here is this is primary only protection first. And again, we're talking about protecting the transformer. That's it. Then in this case, then I would go to 125%. So I'd take whatever my amps value was when we took the kVA divided by the voltage on the primary side. I would take that at 125%, and I would go try to size my overcurrent protective device. Again, no requirement yet for the secondary, this transformer's secondary protection, just primary only protection to protect it in this scenario. So it's 125%, okay? So that's what you see on this table. 125%. And then when we said you can go to the next size up, if it doesn't correspond, okay, that's where this 1 comes from. And this 1 is a footnote that puts you down here. And I don't know that it's not letting me scroll down that far. So I'm going to shut it down and give you the screen so you can see it. Right here. Here's the note, protection. So it says where the 125% of the current does not correspond to the standard rating of the fuser non-adjustable circuit breaker. The higher rating that does not exceed the next higher standard rating shall be permitted. And again, y'all know that we go to 240.6 to find the overcurrent protected devices. Okay, so that allows me to do that. And again, you see right here, primary only protection. 125%, but currents, let's see here, if the current is, we're talking 9 amps or more, right? Then you see here, it's not required, okay? Secondary protection, okay, is not required for that transformer if we follow these rules. However, typically what's going to happen is you're going to, as we said, you're going to end up not doing it like this, right? And you're going to be doing what? You're going to be terminating it into a panel board that's inside of an enclosure. And so when that scenario happens, you have to remember that you also have requirements to protect that panel board. And they may or may not be also considered protecting now the transformer, okay? Because now I'm terminating it into an overcurrent protected device. So although 450.3b does not require secondary overcurrent protection for a transformer, if you're doing primary only protection and you're limiting it to 125 amps, that type of thing, 125%, okay? If you're limiting it, okay, if that's the case, and it says that then 408.36b requires secondary overcurrent for most panel boards, okay? So where a panel board is supplied through a transformer, okay? So this is our typical application, right? Where I put the transformer, I have primary protection of that transformer, and it goes through the transformer. I have secondary conductors, and now I'm feeding a panel board on the secondary side, probably what you do most of the time, right? In that scenario, I also have to protect the panel board. So indirectly, okay, I need to put a breaker in there or fuses to protect the panel board, right? Okay. So in that scenario, requires secondary overcurrent protection for those panel boards. It says where the panel board is supplied through a transformer, locate the overcurrent protection in the transformer's secondary side. Okay, it's 408.36b, and that will be in the panel that it supplies, right? And so it says a panel board supplied by the secondary side of a transformer is considered protected by the overcurrent, okay, protection provided on the transformer's primary side, where that protection complies with 240.21c1. So what does that mean? That's the one allowance, for example, where I'm protecting it primary only, okay? And I meet all the rules that said, okay, look, if it's a single voltage, if I'm just doing a 480 to a 240, right? Or a 240 to a 120, single voltage. If I'm doing that, then guess what? Under the exceptions of 408.36b, then that panel board is considered protected based on the primary protection. And we already know that that protects the transformer. So that is a very unique situation where you would not have to have the protection in the panel board because it's protected on the primary side. Very unique scenario, okay? Caution. Article 450 covers requirements for transformers, not for transformer conductors, okay? So all we're talking about right now is just protecting a transformer. That's it. That's the only protection we're talking about. Now, what we were talking about is a panel board that's supplied from a transformer. Typically, you're going to go into an overcurrent protected device. But there are applications where all of that is considered protected from the primary side if you meet all of the rules, okay, that are involved in 240.21c1, which is the secondary conductor rules, that type of scenario. Okay, we'll look at that a little deeper as we get into some graphics. Let's see here. I was hoping we show a graphic. Okay, so that was the primary protection right here. So this is simply a situation where I have primary only protection and I do not require me to have secondary protection for that transformer. Okay, so I'm not required to have the secondary protection in this scenario. And we're only talking about protecting the transformer. There are other rules in the code which will say, well, I still need to protect my panel board, right? But you saw where there was an exception where that panel board could be protected by the primary only under the exceptions in 408.36b. There are some exceptions for that. Very rare. I don't think in my career I have ever seen where the primary protection that protects the transformer only, and it's not a requirement for the secondary, would have a panel board, and under 408.36 require protection for that panel board, but under the exception, it will say, well, wait a minute, I don't need individual protection for that panel board if you follow all the rules and it's protected on the primary side, okay? And so to look at that, just so you can see it, is we're gonna go to 408, and let's see here, 36, right here, protection. Your protection right here. There you go. Okay. All right. And let's see, where are we at here? Oops, I went too far. Let me scroll. Let me get back to where my thing was. My thing went all the way back to the beginning. For what reason? I don't know. I don't know why I did that, but anyway. Okay. Anyway, so we're looking at here. So this one is B we're talking about. So this is, remember, we're under the overcurrent protection. We're in 408. This is something you may not be aware of. But this one is specifically when it's supplied through a transformer. So where the panel board is supplied, y'all saw me talking about the exception or the allowance. Where the panel board is supplied through a transformer, which is probably almost 10 times out of 10 what you're going to have. All right. Now, here's what it says. It says where a panel board is supplied through a transformer, the overcurrent protection required by 408.36, now read this, shall be located on the transformer, located on the secondary side of the transformer. Okay. And so it's either going to be before it gets to the panel, or it could be in the panel, as long as we're following the secondary conductor rules and the lengths of 10-foot rule, 25-foot rules, secondary conductor rules. The key here is I need to have where a panel is supplied or powered through a transformer, okay, then I have to have that overcurrent protection required by 408.36. That's overcurrent protection for the panel board now, okay, located on the secondary side of the transformer, either before it separately or inside of the panel board. Usually it's going to be a main breaker, okay? That's all we were saying, and that's what you're probably commonly going to do. The exception that it was talking about is right here. This is the exception that I was talking about. It says, look, a panel board supplied by the secondary side of a transformer shall be considered protected. Okay, we're talking about that panel board. It shall be considered protected by the overcurrent protection on the primary side of the transformer where the protection is in accordance with 240.21c1. And what we meant by that is, okay, look, if you're limiting your protection for the transformer to 125% and you only have a single voltage rating, like a 480 to 240 single phase delta, okay. If you have a 240, 120 single phase, okay, and you're dealing with just a 120 single voltage, okay. If you follow all the rules in 450.3b, right, you follow all those rules, you size everything properly, you follow those rules where it's a single voltage on the primary to secondary, then guess what? I'll consider that panel board protected by that primary. And I don't need any overcurrent from those secondary conductors into my panel, okay, to terminate into the panel board, okay? That's all it was saying. It gives you an exception for that, but you have to meet those caveats. Those caveats are very rare, okay? It's not very rare. It's not very often that you're going to see a single voltage transformer that's going to be either a delta to delta or a single phase where you get a 240 to 120 that comes out of there and simply goes into a panel board and then not have any actual overcurrent protection. Okay, very rare. So under that scenario, that is the only case, all of that we just talked about, that is the only situation where the primary only protection for the transformer can serve as double duty and also protect the panel board. You have to meet all those caveats, okay? Single volt, so you got to meet 240.21c4, C1, you got to meet all that. So it's a single voltage output, okay? Got to meet all that. Your primary protection can't exceed 125% that you calculate from the kVA to whatever the primary voltage is, okay? Can't exceed that. And if it does exceed the 125%, you go up to the next standard size, okay? We haven't sized any conductors or anything. We're just talking protection right now. Okay, so that is a rarity, and I went extremely deep into that. So if there's confusion there, remember, we were only talking about primary protection of the transformer, and when the primary protection of the transformer can also protect the secondary and the panel board under those unique conditions. Okay, unique conditions. That's what we were talking about. Okay, now, the day in and day out application that you and I are going to deal with are probably going to have what's called primary protection and secondary protection. Okay, it's typically what you're going to go into. Okay, because most of the output from your transformers are not going to be under 240.21c1. They're going to be either fall under the 10-foot rule, C2, or the 25-foot rule, those type of things, and it's going to probably be 480 in and 240 120 out, or 208 120 out. So you can ignore 240.21c1, and what that means is the primary protection cannot protect the secondary, and you then have to follow the same rules if you happen to terminate it into a panel board. Now you ignore that, and you have to provide the overcurrent protections because the exception will not apply, right? That's what we saw when we looked at the code, when a panel board is supplied through a transformer. So then we're dealing with the everyday stuff that you and I do. Primary protection, transformer, panel on the load side or secondary side of the transformer, and we're going to terminate it into a breaker. And we're going to follow the 10-foot rule. We're going to follow the 25-foot rule. If it's outdoors, we're going to follow the unlimited rule, all those type of things, okay? So we're back to where we are our normal. So again, that's confusing because many people don't deal with that application where you have a single voltage primary and secondary and you have to follow the rules in 240.21c1, but you also have to remember that that's a primary only protection rule and you can't exceed 125%. Okay? And then you would not be required to have protection on the secondary for that transformer. Okay, makes sense? All right, so let's get into what the norm, okay? The norm application. So here's the oh, wait a minute, it didn't go there. So here's the normal application for a transformer, primary and secondary protection, 9 amps or more, 1,000 volts or less type transformer. Number one is look at A. So A is right here. So why does this differ? So this differs because this one now has primary and secondary protection for that transformer. So you're going to be allowed to go up to 250% on the primary. Now, how does this differ from previously where you could go to 125? You can't round up here. You can't say, oh, 250 on a primary doesn't correspond. I'll go to the next standard size. No, it's not how it works here. That's how it worked before, but that's not going to work that way here. Okay, and I can show you that. But let's go to 450 real quick again. Let's see here, 450.3. Okay. All right, so we're going to go to 450.3. We'll just go this way here. So here's our 450.3, and we're dealing with probably this one here, transformers, 1,000 volts, nominal or less, probably what you deal with most of the time. And we're going to be with this table down here, B, right? So you notice this one doesn't have the little asterisk number one, which is the, where the 125%. This has a 3. So a 3 would allow us to possibly exceed the 250%, but that is dealing with special types of transformers. Okay? That is dealing with transformers that are equipped with what's called a coordinated thermal overload protection by the manufacturer. That is already built into the transformer, and if that's the case, then again, that gives you some allowances to go exceed. Okay, so what does that say here? It says in this scenario is that because of this little note that it says the primary overcurrent protection rating or set at a current value that is not more than 6 times the rated current of the transformer, okay, for a transformer having not more than 6% impedance. So we'd have to look at the nameplate, right? We'd have to see what the impedance is of the nameplate. So then we would take the current, so we'd have to do the kVA to the voltage and find out what our rated current is. And then it says, okay, well, if it is not more than a 6% impedance on that transformer's nameplate, then I can go not more than, no rounding up, not more than 6 times the rated current. Okay, so whatever the rated current is times 6, if I can't round up to the next, I'd have to drop down. And the only reason that I can do that is because this is a special type of transformer with what's called coordinated thermal overload protection built into it. It's part of a manufacturer, and you're going to pay for that, okay? Now, what happens if I have impedance that's higher? Well, it says, not more than 4 times the rated current, okay? Not 4 times the rated current, where the impedance is more than 6%, but it is not more than 10%. That would be an extremely inefficient transformer. Probably not going to find any of them like that are going to be more than 10%. Okay, so this allows you to deviate from the 250, but we don't have the same next size up rule. We just has, look, I can use 250, not exceed 250. I could go up to 250% on the primary side if I wanted as a maximum. I can't exceed 250. But then I have these other allowances depending on the impedance of the transformer. So I can go either 6 times the rated current of the transformer if it's not more than 6% impedance, or up to 4 times the rated current where it's not more than 10. So your 10 and 6 are your thresholds. Now, why would I ever have a 250% primary? Well, maybe that transformer is going to be handling has a secondary that's coming off with taps from it. Secondary conductor taps that are tapping it that supply multiple transformers. And the collective inrush that would come from supplying multiple transformers We want to make sure that it doesn't trip out the actual transformers. So under those scenarios, you can go up to 250% on the primary side, but you can't exceed it except where note 3 says based on those conditions, because those unique transformers have built-in components that protect it, okay? That's the only time. So most exams, we just get asked, what's the maximum? If there's a secondary protection, what's the maximum protection on the primary of that transformer? 250%. Now, I'm just talking, but here's some things that you have to be concerned about, prepared for, is that if you go up to 250%, because you're doing the protection of the transformer, you may not adequately be protecting those conductors on the primary side. Okay? So just because you're going up to 250% because you're allowed to protect that protect the transformer, right? Because that's what we're talking about. You may not have conductors that can handle that. Because at the worst case scenario, if it's continuous loads that are taking place in this transformer, then you're basically going to do them at 120. Those conductors on the primary side are going to be at 125% of whatever you calculated the amp rating is. Okay, so if it's 75 kVA divided by 480, and whatever your amps are, let's say 90 amps, then you're going to have to do that at 125% if you determine it's continuous loads, okay, that'll be served by this transformer. And if you do that, you're going to be sizing those conductors, and they're not going to be protected if the primary protection is at 250. So the choice is you're going to either have to increase the size of the conductors, or you don't have to go up as high as 250%. That's a maximum. So typically what people will do is they'll go to 125% for the primary protection of the transformer, and they'll do the conductors at 125%. And that way, if they don't know whether there's continuous loads or not in there, they're going to protect those conductors for continuous load based on the maximum output of that transformer or the maximum current rating of that transformer. And that way they feel safe. And that's what engineers will do. They'll typically just max it at 125. So that you have the disconnecting requirement on the primary that protects the transformer or disconnects the transformer. You have the primary protection, or you have the protection of the transformer on the primary, and then you size the conductors so that they adequately handle the rating of the transformer, but they also are protected by the protection of that transformer. That's typically how we would design it, okay? It makes no sense to do something at 250% and then have conductors that are only sized to 125%. It defeats the purpose, right? Because you may be protecting the transformer, but you're not protecting the conductors, right? And so this is kind of those things that you have to think about. And it may result, if you really need that 250% primary protection for that transformer, then you may need to increase the size of those conductors, which may be increased larger than what the transformer actual current rating is, that type of thing. Right? So now, there are limited factors. There's a limit to what that transformer can output, and everybody wants to get into a discussion like that. But if I'm required to protect those conductors at their ampacity, there's no way that a 250 amp rated overcurrent protective device can protect a conductor that's only sized to 125% of the actual rated load. You get what I'm saying? So we have to follow all of the basic rules for protection. That type of thing. Now, looking at this lesson here, we'll look at different pieces of it here. So unlike note 1, that permits the next standard rating above 125%, again, here you notice that the maximum rating or setting is 250%. So that's what it said in the code, and that's what it says in the table over on 450.3b. Okay, so that's the first part. B, refer to B, which is talking about the transformer right here. So the B call out is saying a transformer equipped with a coordinated thermal overload protection, again, by the manufacturer. It's basically supplied as part of the equipment, and you're going to pay for it. Trust me. It's not a gift from the manufacturer, right? And as we said here, and it's arranged to interrupt the primary current, can have primary overcurrent protection rating or set at a value not more than 6 times the current rating of the transformer, having a not more than 6 impedance, as we saw, and not more than 4 times the rated current of a transformer that has more than 6, but not more than 10, okay, impedance. So that's why you need to know what the nameplate is. I do not see many of this, okay? I've seen a lot of transformers, and I think it's probably primarily due to the cost of the transformer itself, and then dealing with one that might have some coordinated thermal overload protection, and it's costly. So it's typically a standard dry type transformer. It would not have that coordinated thermal overload in it. So you really don't fall into this one here. C is pointing out, let's see, where's C at here? Right here, pointing out the transformer again. So C is saying overcurrent protection for transformers rated 1,000 volts nominal or less, probably the main transformers that you work with, must be provided. Overcurrent protection must be provided in accordance with Table 450.3b. Okay, unless the transformer is installed as a motor control circuit transformer per 430.72C1 through C5, and again, that's there. So that is unique for that application if the transformer is a motor control circuit transformer. Have unique allowances there that you would follow. We're not going to get into that. D, this is the secondary. It says where 125% of the current does not correspond to a standard rated fuse or a non-adjustable circuit breaker rating. And again, we get the note comes back so that we can use the next size up rule. Okay, so this is the example where if the 250% on the primary is a maximum, it can be less. It doesn't have to be 250. That's why I told you most engineers will do it at 125 so that the conductors as well as the protection are aligned together. It's usually what happens. On the secondary side, if they're doing it to 125% and it does not correspond, then you have a note there that is very similar. I'll take you here, and here's your note, right here. And there's your note right there, okay? So here you see your primary up to 250%. Again, this is for currents 9 amperes or more, which is probably most of what you're dealing with. And then over here, you see where it is 125% is the secondary protection of that transformer, not to exceed 125%, but we have a note. And the note's note 1, and the note 1 says, yeah, if you go to 240.6 and it doesn't correspond, I'll let you go to the next size. That's fine. Just can't exceed the next size, but I'll let you go to the next standard size. Okay, that's what it's talking about there. Okay. All right. Yeah, let's see here. Now, it says if secondary overcurrent protection is required, okay, these devices are permitted to consist of not more than 6 circuit breakers or 6 sets of fuses grouped in one location. Now, y'all remember for services, we got rid of that. So you can't have the 6 throws, but it is still acceptable for feeder applications, and it most certainly is still acceptable for the secondary application. So you could feed from the secondary of a transformer, you could feed into main lugs, and then you have 6 separate circuit breakers in there, okay? Grouped in one location. Now, it says where multiple overcurrent devices are implemented, it says the total of all the device ratings must not exceed the single overcurrent device allow value, okay? So what that means at the end of the day is if you're doing a load calculation, let's say this is a 200 amp panel, then I can't have the individual breakers. If I have up to 6 of them, they cannot exceed what would be the requirement if it was a single overcurrent protected device. Yes, I can have the multiples in there, but it's not like you can go crazy, okay? It still cannot exceed the value. Where is that? Okay, now let's go over and look at the code. Where does that say that? And we're over here in the code. And let's see here. Let's go into, oops, back up here, right here. Right? I don't know if you can see this or not, but it says the next higher commercially available rating or setting for fuses and circuit breakers above 1,000. I think I'm in the wrong one. Hold on. Right here. Sorry. Right here. It says where the secondary overcurrent protection is required. Okay. So in this case, where would it be required? Well, required here in one of the examples that may be required is where I'm using the 250% for the primary, then I'm automatically required to have the secondary protection of that transformer, right? And that's going to be most all of your applications, except for what we said when you would do the primary at 125% and then not have any secondary protection. That is very specific applications to meet, and everything has to be met in 240.21C1. All those things have to be strictly met. 1 voltage, again, 480 primary, 240 secondary, 240 primary, 120 secondary, those type of things. On 3-phase, it's delta delta. On a single phase, it's just single phase applications, but only 1 voltage. Otherwise, I'm going to do what? I'm going to be jumping down into the one where I'm going to have primary and secondary protection. And for most all cases, I'm going to be supplying a panel board, and that panel board is going to have to require to have some type of protection. So if I have some protection there, okay, then it's going to kick me into having primary and secondary protection. Okay, so now where does it say here? It says where the secondary conductor protection is required. Okay, and let's assume it is because you're using the 250 option for the primary up to 250, and then you're doing the secondary protection. It says the secondary overcurrent device shall be permitted to consist of not more than 6 circuit breakers or 6 sets of fuses grouped in one location. Okay. Right, so that's where it gets the rules for that. So we still have the 6 and allow. But what it says at the end of that, it says right here, it says the total, I'll scroll down there. It says the total of all devices ratings shall not exceed the allowed value of a single overcurrent device. So again, if this was a 200 amp panel, this is 200 amp secondary, 200 amp panel board protection, and I wanted to have the 6 disconnects, right? I wanted to have that allowance in there. So basically hitting the main lug and then having 6 of the disconnects there. Cumulatively, the total, adding them up just by taking the number that's on the escutcheon, okay, whatever's posted on it, like a 50, a 50, a 50, collectively, they cannot exceed, adding them up, what it would be if you just chose a single breaker to terminate into, okay? So it is limiting you, but it does allow you to have the 6 in a panel board, okay, in a single enclosure, okay? It does allow you to do that. So yes, you can terminate into a main lug only panel if you have 6 breakers, as long as collectively the breakers don't add up to more than what the rating is of the panel board, what it would have been if you had to put a main breaker in there, okay? So it does allow you to do that. That may or may not be beneficial for people. Who knows? Depends on your layout, I guess. All right, so that's kind of the basic rules for that scenario protection. So let me give a real quick summary for those that are still hung around, because I'm sure it confused somebody, okay? Is that if I have a transformer and I want to protect that transformer, but I don't want to have secondary protection, I can primary protection only, as long as I don't exceed 125%. If it doesn't correspond, I can go to the next standard size. And only if the transformer deals with if it's a 3-phase delta delta or a single phase transformer, it has to consist of a 1 voltage. In other words, it can't be a 480, 240, 120. It has to be a 480 to a 240 or a 240 to a 120. It's got to be 1 single voltage. If that's the case, then I can consider that transformer protected, as well as the secondary and the primary, all that protected based on the rules in 240.21C1. As long as I meet all of those, then I'm good to go. Then I can use the primary only protection and not have anything on the secondary, that type of scenario, right? Caveat to that, what if my transformer does not have a single voltage? What if my transformer is dual voltage, multi-voltage, 120, 240, 208, 120, things like that? Well, then I cannot use the primary only protection application to protect that panel board either. So now I'd have to have protection under 408.36. I have to have protection in that panel board, okay? That type of scenario, right? Now, in that scenario, if I want to use, okay, now that I have protection at panel board, or I have a panel board and I can't meet the requirements of 240.21c1 because of the voltage classes, or what voltage we're dealing with, now I have a panel board, I'm gonna have protection for that panel board, and now I kick into where I can go up to 250% on the primary. I don't have to go to 250. I can go to 250, but that kicks me into having primary and secondary protection of that transformer. So the primary protection of the transformer can go up to 250%. Does it have to go to 250? No. Most engineers will simply take it to 125. Why? Because when you take the conductors on the primary side, we're going to take whatever the amp rating is of that transformer that's rating and do it at 125% because we may or may not have continuous loads in there or not. Most engineers are not going to care. They're going to simply size those conductors on the primary at 125%. They're going to size their overcurrent protection for the transformer at 125%. It's going to serve double duty and also protect the primary conductors. And it's also going to be the disconnecting means requirement. Okay? Get me? All that kind of works together. On the secondary side, is saying we're coming out of transformer, assuming we're following our tap rules, 10-foot, or secondary conductor rules, I should say, 10-foot or 25-foot, they're going to typically terminate, let's say, into a panel board, which is in an enclosure. Well, in that case, I'm allowed to go up to 250%, and if it doesn't correspond, then I'm going to go to the next standard size. Remember, when sizing transformers, we need to do a load calculation. We don't just willy-nilly this. You don't determine your kVA of a transformer just because you just go, I'll just make it a 75. I'll just make it a 50. I'll just make it a 25. You got to know what loads are being handled by that secondary, right? We need to know what it is that's being loaded so that we can size the panels that are being supplied by these transformers. So if I know that I got a 200 amp panel that's going to be adequate enough in size to handle the loads that are going to be in this building or whatever's going to be on that second supplied from this transformer, I got to know that I sized the panel right. So I have to do a load calc. Once I've done that load calc, I've sized my panel. Now I make sure that my transformer can handle the output that will handle the loads that I calculated that I did in order to choose the type of panel or the size of the panel I wanted. Okay? Makes sense? Okay. So once I've done all that, then I can choose the size transformer. Now, can I have a transformer that's much larger than what's needed? So maybe I calculated out and I need a 50 kVA transformer. Can I put a 75? Can I put a larger transformer in? Absolutely, you can. Maybe you're doing it for expansion. Maybe you're putting a larger one in because that's just what the engineer spec'd, but the load calc says I didn't need that big a one. That's fine because a transformer can supply multiple secondary loads. It can do multiple panels. That's not a problem. Okay, as long as you size your transformer properly. Okay, now, as far as those transformers, just a little tip when it comes to those secondary conductors, because we didn't talk about the conductors. When it comes to secondary conductors, if they're terminating into an overcurrent protected device, right? Like let's just say they terminate into a 400 amp breaker, okay? Or a 400 rated piece of equipment. Then those secondary conductors, you're not allowed to use the next size up rule. Those secondary conductors have to be sized based on the overcurrent protected device that they terminate into. And it's assumed that you calculated the load based and sized your panel based on that. But for a good example of that is if I have a 400 amp panel that I'm supplying from a transformer secondary. And I'm thinking, well, I'll just run, I'll just run me some, let's see, what do I want to say? A 500 kc mil copper. And you go look at it under the 75, you'll look at it, and I believe it's 380 amps. And you're thinking, what? No harm, no foul. What the crap? I'll just terminate that. I'll just use the next size up rule. You can't do that because it's not allowed for you to do that under 240.21c. And that is where we're sizing secondary conductors. Okay. So what does that mean? Well, that means that I'm going to have to make those secondary conductors have an ampacity value that is equal to or greater than the overcurrent device that I'm terminating into. So if that's a 400 amp breaker that's in that secondary panel, then those secondary conductors have to have an ampacity of at least 400 amps. Can it be greater than that? Absolutely. Can it be less than that? Absolutely not. You do not get the allowance to do the next size up rule. Okay? Doesn't work. Now, here's an interesting thing. That is okay on the primary side, right? That is not okay on the secondary side, right? So keeping those things in all those things in line, right? Specifically doesn't allow me to do that. Okay. Anyway, where were we at? Let's see here. I don't know if there's any more pictures. I'm sure. Let me see if there's. I want to see if there's anything that covers. Oh yeah, let's go on and cover this real quick because I have some people that posted it in the chat, and it went so quickly that I couldn't see all of that. So let's talk about the grounding and bonding requirements here. So this is a transformer here. So grounding and bonding terminations in the panel. So let's just say it's a transformer, it's supplying a panel. And everybody wants to know what the bonding and grounding requirements are. Okay, so premise wiring system is defined as interior or exterior wiring, including power, lighting control, and signaling wirings together with all their associated hardware, fittings, wiring devices, both permanently and temporarily installed. That's another thing that people lose sight of all the time is they think when you do something temporary that you still don't have to follow the code. You most certainly do. One of the biggest aspects I get from people all the time is, not to deviate away from the discussion, but temporary poles, services for temporary job site construction. So many people think, and maybe your jurisdiction allows it, but people think, for example, if I'm going to be driving ground rods, they think that I only need to drive one because it's temporary. It says that nowhere in the code. You treat that service, whether you like it or not, you treat it as a service, whether it's temporary or not. It doesn't matter. The electrons don't know any different. Lightning doesn't know any different, okay? We don't know what's going to be plugged into that temporary service, but it's still a service. So even if you go to 590, it's going to tell you that you still have to install services in accordance with 230, right? And 230 is going to tell you to install it, and it's going to establish, we have to establish a grounding electrode system. So if you're using ground rods, you'll end up back at 250, and you'll be back at 250.52, right? And at the end of the day, you're still going to have to, if you can't prove that one ground rod is 25 ohms or less, then you're going to have to install 2 ground rods, whether you like it or not. Now, maybe you have a local amendment. Maybe some jurisdiction says, 1 is fine. That type of thing. Maybe an inspector says, I don't care about that. I don't get into localities, and I don't care about what you do in your locality. I don't care. I'm just telling you what the code says. The code says you're going to establish a grounding electrode system. If you're going to use ground rods, unless you can prove 25 ohms or less to one ground rod, then you're going to install another ground rod, and you're going to be at least 6 feet away, okay? And it's going to be 8 foot driven into the earth unless you hit rock. If you hit rock, then you're allowed to go up to a 45 degree. If you hit rock again, then you're allowed to lay it in a trench in that succession. So many people go straight to the trench. You can't go straight to the trench. Got to drive it. If you can't drive it, 45. And by God means don't cut it off. Because I've seen that being done lately in videos people are sharing. Don't do that, okay? All right, back to the lesson here, because I want to cover grounding and bonding before we go today, so it's going to be a little longer today. Plus, I've been gone for 3 or 4 days, so bear with me. All right, so what does this include? It includes wiring from the service point or power source to the outlets, or wiring from and including the power source to outlets where there is no service point, okay? So, again, all this is saying is at the end of the day, temporary has no rules when it comes to this. You have temporary allowances for using certain types of wiring methods up in 590, right? Okay, but that's it, okay? Miguel passed your exam. Congratulations. Good job, Miguel. All right, so such wiring does not include wiring internal to appliances, luminaires, motors, controllers, whatever. We're not talking about the internal. Premise wiring is all of the external. Everything's from box to box, from utilization equipment to outlet box, then from outlet box to the panel, that type of thing. That's all the stuff we're talking about, right? A grounded circuit conductor can be used to ground non-current carrying metal parts of equipment, raceways, and other enclosures on the supply side, okay, or within the enclosure of a main disconnecting means or overcurrent devices of a separately derived system. That's where we typically would see our system bonding jumper, okay? So we have some allowances there in 250.30A1. And we also get the allowance to use the grounded conductor to bond things on the supply side. If you're not familiar with that, God's sakes, go watch my video on how to do supply side bonding, because you can, and we very commonly use the neutral, which is probably more properly termed the grounded conductor, because we know all neutrals are grounded, but not all grounded conductors are neutral. So on the supply side, we do that at cabinets and wireways that service conductors are in. We do all this stuff in 250.92. Okay, but not on the load side, except an example here at a transformer where you're allowed to put in what's called a system bonding jumper that would connect XO to case in that scenario. That is one of the allowances downstream where you're supplying a transformer where you could do that. Okay, now, as far as that system bonding jumper, that connection, and I'll show you in an example here real quick, right here, okay, from here XO, down to here, okay? I could have the system bonding jumper right here. And that's going to connect, again, this is in a transformer. That could connect the XO to the frame or to the case. That is that allowance in 250.30, okay? But I also have an option to do it here at the first disconnecting means location, right here on the secondary side. Right? So I have an option to do it here or do it here. Now, there's an obscure allowance for you to do it at both locations as long as there's not a conductive path between it. But as you can tell right here, this looks like FMC, so it most certainly is a conductive path. So not gonna be here and here. So I don't want to see a system bonding jumper in here, folks. And then you get to this first panel and you leave in that green screw. Don't do it. And this is probably where people already know that you don't do this with a remote distribution panel, right? Separate. That's why we run 4 conductors, right? But in this scenario, many people may get confused at a transformer and just leave that in there thinking that they need that there. Not if your system bonding jumper is installed down here. Yes, you need it if you're going to be doing it right here. And the code allows for you to do it at either or. Just typically not both, unless you can meet the rules, it's non-conductive paths between them, that type of thing, and you're not creating any objectionable currents, then you could have it at both locations. But again, for the most part, either or, here or here, either one, okay, but not both. All right, so that's where we go there. So here, what we're gonna do is in our case, we're gonna show it says an unspliced system bonding jumper, an SBJ, which, by the way, we're getting rid of a lot of acronyms in the future codes because everybody doesn't have they're not grown-ups and they see something like a bonding jumper and start acting like a child. And it's actually brought up that way, people acting like a child. Okay, I said BJ, whatever. All right, so an unspliced system bonding jumper shall comply with 250.28A through D. So this is going to talk about the type of connection, copper, aluminum, what it needs to be, all those type of things, and sizing, by the way, which is ultimately going to send you to 250.102C1 for sizing. It says, this connection shall be made at any single point on the separately derived system from the source that is in the transformer to the first disconnecting means, okay? Which in this case, I'll just highlight that, which in this case is right here. Here's a transformer. This is the source, okay? These are called derived conductors because they're not intimate with the primary. The grounding and bonding is, but again, in separately derived system, it's the primary conductors and secondary conductors, okay, that through the transformer, they are not intimate, okay? They're isolated from each other, right? And so they're not connected together. And anyway, if they were, they would short out. We'd have problems. So here it's chose to be done here rather than here. It's your choice. Most people do it down here. They'll put the system bonding jumper in it. Just make sure you don't do both, because you don't, in this case, you see it's a metallic path and you're going to cause problems. And you see right here that there is a conductor running through right here, right? Okay, so this is your system bonding jumper right here. And you see this conductor running through right here, running all the way through, right? Okay. All right, just want to make sure we're covering everything. Okay, that's your supply side bonding jumper. All right, so anyway, let's get back down here where we're at. Okay, now, it says the system bonding jumper shall remain within the enclosure where it originates. Okay, that makes sense. So wherever I put the system bonding jumper in, it stays there. Well, that's a no-brainer, wherever you put it. So if you put it from the XO to case in the transformer, that's done. If you put it in the first panel, that's where it's done, okay? Now, here is one that people ask about. What if the source, this transformer, is actually located outside of the building or the structure it supplies, okay? And we're not talking utility here, okay? We're talking about, let's say it's a premise transformer. It's stuck outside the building, and that's where the source is. And then it comes into a panel that's located, okay? Because these are like secondary conductors. Okay, they're not service conductors. If it's a premise transformer, it's not service. Okay, so say it's located outside, and then it says a system bonding jumper shall be installed at the grounding electrode connection in accordance with 250.30C. Okay, so wherever we're installing that grounding electrode connection, that is where we're going to install the system bonding jumper. Okay. And you see it says A, and it calls out A right there. This just happens to be right there. That is the system bonding jumper installed right here. So here you see what? That is where the grounding electrode conductor that's going out to whatever the electrode is for that structure, that's going out to it, okay? Or anything that extends that connection, right? So that's what it's doing right here. That's why it's here, okay? And you don't see it here, okay? Wherever that connection is being made, okay? Typically, the system bonding jumper is installed in here. And so typically out of here is where you're going to see them take this out, okay, and go out to the electrodes, okay? So important, where is the system bonding jumper being installed, okay? Important aspect of it. All right, so let's see here. Okay, so that was, say now, C, for vertically operated circuit breaker handles in the up position. Okay, we don't really need to look at that, but that's 240.81. That is basically referring over here. And obviously, the only important thing I'll bring up about this is orientation of panel boards, right? So the NEC only cares when it's a circuit breaker that is operated vertically. If it's horizontally, doesn't matter, and typically those panels will be clear that it could be upside down or either way, up or flipped, okay? Doesn't matter. If you see the verbiage in it and you can read it and it has it in both directions this way, or if you flipped it, you can read it this way, then typically that's going to be, doesn't matter. And it's very common to turn a panel so that the breaker's closer to reduce the length of the conductors, okay? And having to run conductors through the enclosure all the way up to the top of the breaker. Now, if it allows you to do that, if it is a horizontal mounted circuit breaker, then it is fine, okay? But if it is on, off marked, and it is being installed vertically, it has to be on in the up position in accordance with 240.81, I believe. All right, where are we at? Yeah, right there. Oops, sorry. You're not looking at the lesson. My bad. Right here. So that's your on in the up position requirement, okay? Next, it says D. It says a grounded separately derived AC system shall comply with 250.30A1 through A8 unless it is an impedance grounded neutral system installed as specified in 250.36 or 250.187 as applicable in 250.30A. Okay, so separately derived systems, okay, we have to follow all the rules just like it was a normal system. We're going to have to establish a grounding electrode system. The only difference is you do have what's called impedance grounded neutral systems, which make its connection virtually to Earth through a high impedance, an impedance device. Okay, and those are called impedance grounded neutral systems. Okay, and if that's the case, they're installed a little differently, and typically between the grounding electrode conductor and the XO, there is an impedance device right there. Okay, that type of thing. And those are typically used on systems where they don't want, they want the system to be maintained and run longer and not have an issue with it. Okay, let's see here. Actually, let me take that back. This actually impedance grounded neutral is actually installed between the XO. Okay, so it makes a connection in there and adds this impedance in there so that things don't trip off prematurely or dealing with those type of systems. Either way, you do have to follow their specific rules in 250.36 or 250.187. Okay. Let's see here. Let's see, E call out. Okay, so this is just the equipment grounded conductor, by the way. And I don't know if you can see this, and I can blow it up, but I don't know how large this will get on the illustration. Bear with me. I'll show you if it lets me zoom in on it. Kinda. Okay. So this is the equipment grounding conductor here. It's actually running, they don't show it real well. It's not running to a lug. It's actually running with, so it came from the primary side because obviously this armor is too large. The sizing is large. It would not be allowed to be part of the equipment grounding conductor path or effective ground fault current path. So it's bonded. You notice there's no loop here. There's no running it through a lay-in lug. This is a pure punched out KO. Everything's fine, this type of scenario. But you did have to run an equipment grounding conductor through there because it still has to clear an overcurrent protected device on the primary side. Okay, so let's see here. Now, if I can get this to go back to normal size. Okay, back to normal. There we go, back to normal side. Okay, and then you'll also notice over here, I guess I can zoom in here a little bit. You'll notice over here that this is a punched KO, and you don't see any lay-in. What you see is because this is flexible, it is bonded at each end. Okay, it is bonded. Okay, but you had to run a supply side bonding jumper up, over, and make the connection here. Okay, see that? So that maintains the integrity between here and here. Okay, we're not relying on this here because typically this is FMC and it's size, and it's bonded because it's a KO and it's punched out. There's no need for a lay-in lug here. Okay, as long as you're using a listed fitting, listed wiring method, we're not using it as an equipment grounded conductor. We're just meeting the bonding elements here. Okay, and you're typically not. Now, you could run into something on this end which may be impaired. Okay, concentric, eccentric, something like that. The best advice here is remove it and just treat it as its non-impairment. And if that's the scenario, again, you only have to get into advanced bonding requirements if it is dealing with over 250 volts to ground. Now, chances are this one's not. This would probably be like a 208 120 or a 240 120 because of the color scheming, although this is not a requirement of the code. But typically, in looking at this, this is probably going to be feeding a 120 208 panel. So if that's the case, concentric, eccentrics aren't going to affect anything. And your fittings are all going to be listed anyway for this type of wiring method, whether it's FMC or whatever it would be. So just normal lock nut, normal bonding is all that's necessary. Don't have to worry about it because this is chances are, again, it's not over 250 volts to ground, that type of scenario. And these obviously are not service conductors. So again, it's a standard, cut the hole and done. Now, even if you had concentric or eccentric, there's a high probability that these are not over 250 volts to ground. So normal lock nuts would be fine. Everything else would be fine, and they'd be considered bonded because you're using all listed components. But because this can't be utilized because of flexibility, then that's when you would install a supply side bonding jumper in here, okay? And that's where it connects, right there. Makes sense? All right, where are we at? Let's get back up to our examples here. Where are we at? Okay, all right, so that's done. Let's see, right here, E. What is E? So E is right here. So this is the equipment grounding conductor that's coming with the primary conductors, right? All right, so E, it says, again, we're talking grounding and bonding now. It says, size of the equipment grounding conductor in accordance with 250.122. The equipment grounding conductor must be of the type listed in 250.118A. And if you go look at 250.118A, that is the wire type in this scenario. And why is that? Because this is too large. This would not qualify as an equipment grounding conductor. Okay. So we're going to have a wire type in there. A. Bare, covered, or insulated. Okay. Doesn't have to be insulated. Okay. But if it is insulated, it's got to be green. Okay. Could be green with a yellow stripe, whatnot. It looks like we lost LinkedIn. We lost LinkedIn. So if anybody's watching from LinkedIn, it just arbitrarily failed on us, that type of thing. So there you go. All right, so let's go continue on. Okay. F. What is F? F is right here. Okay. All right. What's F talking about? It says, if a building or structure is supplied by a feeder from an outdoor separately derived system, okay, it says a system bonding jumper at both the source and the first disconnected means is permitted. All right, so it's a permissive, right? If it's outdoor and indoor, typically we might see something outdoor and you're thinking that's outdoor, it's remote, right? And you put a system bonding jumper there and you're thinking, well, that's remote. Now I come to the panel that's inside. Can I put a system bonding jumper in there? Remember what I said other times, it's discouraged? But again, here's the example of where it would be permitted to do both, but you got to meet these caveats. And what are they? So it's permitted to put that system bonding jumper outside of the transformer and inside as well. But if you do that, you do so, it does not establish a parallel path for the grounded conductor. And I'm not sure how that would do that, right? If you do it that way, you have to make sure, do I have mutual conductive paths for that grounded conductor connected at both ends? Is that going to create that, right? Now, if it does, then you have a problem because you can't establish those parallel paths. So you do what you can do to remove that. So you choose which one you want to do. And like we said before, you can do it at the source or you can do it at the first means of disconnect. And that is where your GEC would go. Okay. Now, while grounded conductors used in this manner shall not be smaller than the size specified for the system bonding jumper. Okay. So a minimum sizing requirement. Okay. It says they do not have to be larger than larger than the ungrounded conductors. Okay. So those conductors that are coming from the outside transformer to the inside location, say a panel board inside, then again, it's got to be at least sized what? Okay. It's got to at least be sized for the grounded conductor, not smaller than that, but can't be smaller than the system bonding jumper. But this conductor does not need to be larger than the largest ungrounded conductor that's in that raceway. Okay. So I don't have a picture to show this, but if this transformer was outside, we're talking about this grounded conductor right here. Now, first of all, it has to be sized to handle the load, right? We know that, okay? That's the first thing, okay? And we know, secondly, it can't be smaller than the size specified for the system bonding jumper, which is still going to be based on 251.02C1, based on the derived conductors. So, okay, it can be smaller than that, okay? But in all cases, it does not have, that grounded conductor does not have to be larger than the largest ungrounded conductor, okay? Now, in applying this exception, connections to the earth do not qualify as providing a parallel path. Absolutely not. Never would use the earth as a path at all. So again, make sure you're fully clear on that. The earth is never. Now, utility folks, yeah, they can use the earth, okay? Because their overcurrent protected devices are so much smaller, okay? And the voltage is so much higher, okay? Doing Ohm's law will tell you that it will be fine. But for our case, it's not going to work, right? So we can't use the earth for that. G. So G is right here. So here's the XO in this transformer, okay? In G, it says grounding and bonding terminations made at the system disconnecting means or the overcurrent device required that the transformer's grounded neutral bus be insulated from the transformer enclosure. Okay, so if you do want to make that connection, okay, over in the panel instead of in the transformer, that's fine. Remember what we said? You're not going to make this connection from here over to here. You're just going to leave out the system bonding jumper. Why? Because we did it right here. Okay, that's a no-brainer, right? Then it says, if the neutral bus is bonded to the enclosure and the raceway to the panel board is metallic, then part of the neutral current flows on the raceway. Okay, and again, that would be prohibited because that creates objectionable currents that actually can cause current to flow in paths that were unintended, but it can also cause it to flow on paths that are something that you could come in contact that are part of the grounding and bonding system. And that's not what we want, okay? So again, long story short, just like you've learned before, you either do it here or you do it here, okay? We don't want to create problems where we have circulating currents and objectionable currents. And it's not just about how it can affect the operation of sensitive electronic equipment. It again is literally going to put flow of current on metal parts. Now, one of the things to remember that current flows due to differences of potential. And so when you hear somebody say that current flows on the path of least resistance, that's incorrect. It flows on all available paths, proportional to the amount of impedance on that path. So obviously a low impedance path, more current will flow. Makes sense, right? If there's more impedance, what is impedance? It's objection to current flow. So not as much current, okay? So obviously what we don't want is to connect it to these metal parts, which we are required by the code to construct a low impedance effective ground fault current path. So it's already tying all these metal parts together to be low impedance. The last thing we want to do is impose potential voltage and current over onto these metal paths. That would be a problem, right? Because all it's doing is what happens if there's a loose connection somewhere? And then you come and get in contact with that loose connection and you make that connection. Well, depending on how you come in contact with it, that's going to be all she wrote for you, okay? So hopefully that never comes into play with anybody, but it can happen. All right, now H, the last one, and that is right here. These are your terminations for your equipment grounds. This is where your termination for your supply side bonding jumper that's going up with this raceway that again doesn't qualify because it is flexible. So it requires a wire type supply side bonding jumper to go with it, okay? But also this bus could be where the XO puts the supply side bonding jumper over here. Also, just for making sure folks are clear, when you look at a transformer, you install it, you'll sometimes see these little straps and things that are on there that connect to the frame and over. Do not assume that that is a system bonding jumper, okay? Typically, it's going to be a wire or some kind of bar or some kind of metal bus. It's going to be integral into it. Doesn't necessarily mean it's that little copper strap or this little strap. Don't assume anything. Look at the literature for the transformer to determine whether or not that is the system bonding jumper that is pre-installed or not. Okay? Don't take anything for granted. I've seen many applications where that was misunderstood and the system bonding jumper was grossly undersized because they thought that little strap was all that was necessary. Okay? Just be careful. Make sure you understand. Just don't get in there blindly slap these things in. I know you don't. Y'all are very technical. I know. So I know you wouldn't do that. Okay. All right. So H says, where separate equipment grounding conductors and supply side bonding jumpers, which is what we talked about, that's going up to the first disconnecting me. That's a supply side bonding jumper, are installed. It says a terminal bar for all grounding and bonding conductor connections shall be secured inside the transformer enclosure. The terminal bars shall be bonded to the enclosure in accordance with 250.12 and shall not be installed on or over any vented portions of the enclosure. That's in 450.10a. Remember, folks, we give you these chevrons for a reason. These are low-hanging fruit on exams, but the key thing is sometimes when you're adding this terminal bus, if it doesn't come with one in the bottom of the enclosure, be careful where you install it because you have venting in the bottom. Just because you have those nice little slots there that you can put the bar on, put a washer on, and put a nut underneath, does not mean you can do that, right? Those are for venting. Right? We can't have anything that obstruct the venting to keep that transformer cool, okay? Now, the more efficient the transformer is, the more cooler it is going to be, okay? But you all know the stories of being in machine rooms and transformer rooms when it's just so hot in there because those transformers, due to hysteresis losses and the heat that builds up because of they're very efficient, but that inefficiency of them is what generates the byproduct of heat. And so we need to make sure that they're vented, okay? That type of thing. So we don't want to obscure any of the venting, okay? So there may be already one installed down there for you. It may be that you have to drill holes and follow the requirements for mounting it in 250.8, follow the rules in 250.12, and add your own. But most of the transformers that I run into, they put a bus down there already. And if it's already manufacturer installed, then I'm gonna use it. That's what I'm gonna use. Okay. All right. Let's see if there's anything else for the grounding and bonding. Let's see here. Let's see if we got a picture here. Yeah. So that one was one. Let's show you the example. Let's show you the same example here. I might as well cover both. So here's grounding and bonding terminating in the transformer. So then my most favorite place to do it is in the transformer. And then we separate the conductors in this panel that it supplies, right? That's typically what you're going to do with a transformer. Most of the time you're supplying a panel to have additional loads. So in there, separate neutrals and grounds, everything, just like you would for a remote distribution panel in a garage or in a basement or whatnot, running 4 conductors up. You isolate the neutrals and you connect the equipment grounds to the case, right? Separation, very common. We all follow that rule. But what happens, what about, now, that's when I put the system bonding jumper actually in the transformer, okay? So now, while the illustration that we're gonna look at is showing 3-phase separately derived system, it's just an illustration. Don't think that this is not the same rules that would apply to a single phase system. Exactly the same rules, okay? When it comes to the grounding and bonding, exactly the same type of methods and rules, right? Just think, electrons don't care. So you follow all the same rules, so don't make it overly complicated, okay? So let's see here. For A, it's calling out right here. Right? And you notice something right here, okay? The system bonding jumper is not installed. It's being chosen to be installed here, right? And it's going to be sized based on these derived conductors right here, by the way, in case you didn't know, right? And ultimately, the system bonding jumper 250.28, A, B, C, and D is going to ultimately send you to sizing 250.102C, okay? But this is sized right here. And this is the system bonding jumper right here. So we do it here, right? And we're not doing it here. You'll also notice something else. The grounding electrode conductor going out to the electrode for this transformer is from here, where the system bonding jumper is installed. Not here, like on the last one. That was only if I chose to put the system bonding jumper here. So it's being done down here, see? Right there. And then here is where it's going out to the grounding electrode, right here. So this is your grounding electrode conductor. It's going out, okay? And this, again, is your bonding jumper right here. That is your system bonding jumper, okay? Kind of paraphrasing all these so we can run through these. All right, so that was A. It says, if the grounded and bonding termination is made in the transformer, the system disconnecting means grounded neutral bus must be isolated from both the panel board enclosure and the equipment grounding conductor. So it's isolated. Y'all got that. We just covered that. Okay. Again, if you do it improperly, somebody asks what happens. What if I accidentally leave the green screw in the panel bonding the neutral to the enclosure, and then down into the transformer, I put in the system bonding jumper? Well, what's going to happen is you're going to get circulating current. And that's going to be a violation of 250.6a, and it's a prohibited act. So the code mandates that we remove that scenario. So the simple task is to remove the green screw that's in the panel and to make sure that we isolate the neutral. Okay, makes sense? Okay, so we're prohibited from doing that. Now, B is talking about right here. Okay, so we got B right here. And let's see what it's referring to. It says, except as permitted in 250.30A1, 250.32B1, exception 1, and Part 10 of Article 250, okay, except as in those permitted allowances, it says a grounded circuit conductor shall not be used for grounding non-current carrying metal equipment parts on the load side of a separately derived system's disconnecting means, okay, for a separately derived system having no main disconnect, okay? All right, so remember where I said you could use the grounded conductor in 250.142A to bond metal parts on the supply side? You're prohibited from doing anything like that except in 250.30A1, 250.32B1, exception 1. And you remember that's the old rule where you had a detached structure and you could use a neutral conductor to do that, but that was like 1995. It was a long time ago. Not anymore. Now you have to separate grounds and neutrals at a remote distribution panel. But years ago, it was an allowed practice under the exception, okay? All right, so anyway, so accepting those accepted practices, the everyday rule for you and me is that I do not want that neutral connected to the enclosure. I need it to be floating in this case because we put the system bonding jumper down in the transformer. That's why we did it, okay? Now, C is referring to right here. So this is the transformer rule. And here's what it's saying. It says, the system bonding jumper connection can be made at any point on the separately derived system from the source to the first disconnecting means, or in our case, it would be the overcurrent protective device in that first panel. This is in either panel or the transformer. Okay, so that was the rule we talked about earlier. Not both, one or the other. Because typically doing it in both could create problems, again, with objectionable currents, that type of scenario. So that's what we're doing. So in this case, we chose to put it where? In the transformer, not in the panel in this example. D, what is D? D is talking about right here, this connection. So D obviously is talking about the system bonding jumper. So it says here, it says a grounding, oh, no, it's talking about the other conductor. It says a grounding electrode conductor, okay, grounding electrode conductor for a single separately derived system, okay. Oh, okay, so it's going to talk about the grounding electrode conductor. Shall be sized in accordance with 250.66, okay, because we are sizing grounding electrode conductors. That's what that article is for, okay. For the derived ungrounded conductors, okay, remember the derived conductors are those that are coming off the secondary. They're being derived, if you will, from the transformer. Says, it shall be used to connect the grounded conductor of a derived system to the grounding electrode in accordance with 250.30A4 or as permitted in 250.68 C1 and C2. So that is some allowances for connecting to a water line under specific conditions or to building steel that will extend that connection to the electrode. So you have some allowances, and again, that's important because you could have transformers on multiple freaking floors, okay? So that does give you some allowances there. Now, this connection shall be made at the same point on the separately derived system where that system bonding jumper is installed. So let me show you what it's talking about. So right here. So this connection right here, right, is connected over to here, right, through this system bonding jumper, right? All of that is connecting to here, the grounding electrode conductor right here. So it makes all of this intimate. That's why it's so important to size the system bonding jumper properly. So here, all these connections are intimate, and then it goes from here, right? You see that? Now look right in here. It requires us, I don't know if I can zoom in on this. I don't know if I can see it or not. Let's see if I can maybe zoom in a little bit so you can see it right here. So what you see here is all this connection here. And here's your grounding electrode conductor right here. Okay, coming over. All this is intimate, all tied together because of a properly sized system bonding jumper. Okay, this conductor right here, the grounding electrode conductor that's going out to, let's say, the electrodes, or it could be going to the water pipe system if you meet its rules, or it's going out to the building steel, like the I-beams, the inner framing, all of that under those caveats in 250.68. But it is sized based on the derived conductors, and that's these, and you go to 250.66, and that's what's going to size this. Okay? Make sense? And again, notice how this all works together, and we're giving you enough terminations here to be able to make this happen. Okay, let me see if I can get me down to 100%. I don't know if that's 100% or not. Okay, anyway, works for me. All right, so that's that. Let's see, where are we at now? That was, what was that? That was D. E says, okay, now E, in this separately derived system we're doing, it says E is an unspliced system bonding jumper that complies with 250.28A through D. Again, that's going to tell you the material you can use, and it's going to give you directions on sizing, which ultimately, again, at the end of the day, is going to send you to 250.102C1. But all that starts there when it comes to sizing, okay? And so that is this conductor right here. All right. Next, it says the grounding electrode conductor, that's F, which is right here. This conductor right here, right? See, coming over here to this bus. That we saw, again, that is what? That is the grounding electrode conductor. The installation, okay, we already dealt with the sizing. The installation must comply with 250.64A, B, C, and E, and 250.30A7. Okay, so the grounding electrode conductor shall not be installed through ventilated openings and enclosures. So that's another aspect of it. So we have to meet the rules. Now, this has to do with things like, what does all this mean? So all of that has to do with how it gets from point A to point B on the installation process, okay? Remembering if you're running it through a ferrous raceway that you're going to have to bond it at each end, all those type of things. So those are the installation requirements that you have to meet. And you have to make sure that you just qualify and meet all of the rules on 250.64A. Another one of this might have to do with termination. For example, if you want to run an aluminum, okay, equipment, grounding electrode conductor, if you want to run an aluminum one, you can. The code allows for it. However, when you terminate it, depending on the electrode, you can't terminate it within 18 inches of the earth unless you're terminating it in an enclosure that is rated for the environment, like a NEMA 3R, and it provides you that termination, then it could be less than 18 inches. But other than that, it's not going to be closer than 18 inches of the earth. If you're terminating it outside on a bus, and then it's going from the bus out to the various electrodes, that's okay, fine, but you have to make sure that termination is at least 18 inches from the earth, okay? That's what you get on those installation requirements in 250.64. A, B, C, and E, and all that kind of stuff. And again, E is talking about if you happen to be doing it with ferrous raceways that are protecting that grounding electrode conductor. My recommendation, don't do it. Don't use a ferrous raceway to do that. Use Schedule 80 PVC. It's perfectly fine, and it eliminates all that other bonding crap that you got to deal with. It's just my advice to you. Okay. Now, a lot of people want to take that grounding electrode conductor and conveniently just drop it out those vent holes. It specifically tells you you can't do that. We cannot have anything going out of openings that are not intended for those openings, right? So a mounting hole that you would mount something is not designed to run a conductor through. That's a mounting hole. That's what it was part of the evaluation of that equipment, okay? Now, panels have a little teeny hole. You knock that out, you run the GEC through that, that's fine. Doesn't need to be clamped to the enclosure because of the size, okay? And it's a little thing called Passion's Law. It's typically fine. But where you run it through a big knockout, then you're going to have to take it through a connector. A lot of people say, well, I'll just use a Kenny clamp. You can if you want to, all right? But at the end of the day, you have to make sure you don't want to use a non-metallic sheath cable fitting that is not designed to be used to take a grounding electrode conductor through it. Check with your manufacturers, okay? Marlon says, couldn't we also take the half ground electrode to the... I don't know what you're asking, Marlon. I'm sorry. I don't know what you're asking. I don't know what a half ground electrode is. A half inch. I'm not sure what you're saying. All right. So anyway, let's see here. I don't do slang, guys. You got to be very specific with your questions. Give me all the details, even the name of what you're talking about. Okay. Speculation kills me sometimes. All right. So don't run it through vent holes. Now, G, what is G? So G is right here. It's called bonding jumper installed right here. That's the G. So we know that's why that's being installed. It says, if the system bonding jumper specified in 250.30A1 is a wire or bus bar, okay, so a wire or bus bar type, it says it shall be permitted to connect the grounding electrode conductor to the equipment grounding terminal bar or bus if the equipment grounding terminal bar or bus is of sufficient size for the separately derived system, okay? So basically what this is saying is that I could take, if you look back here in G, okay, where the system bonding jumper is of the wire or bus bar type, okay? So that's what this one is, by the way. This is a wire type, okay? Could be integral bus bar. It's made in there, does the connection by linkage, could be, but that's of the wire type. What it's basically saying is, I'm permitted to take my grounding electrode conductor, okay? So instead of, let me show you right here. So instead of taking it here, I'm permitted to take it here, right? Because this is of adequate size. Otherwise, I would take it to here. So I'm permitted to take it here because I properly sized, and this is of the wire type, and I adequately sized the system bonding jumper, okay? Now, what else? Let's see if there's anything else in H. It's just talking about the bus here, okay? So where the separately, what's this says, let's see here. Oh, we're back in G still. G is, okay, we're still talking about the use of this jumper. Let's see here. So it is permitted to connect the grounding electrode conductor to the equipment grounding terminal bar. So I could have taken, that's why I can take it here. So that's why this right here, if you see this, this is why this is right here. Why is that important? The reason that's important because in a panel, people ask all the time about making connections. You know, I've shown you some panels before where my neutral bus and my equipment grounding bus are tied together with a wire, right? They're not all on one connection. They're connected together, right? So with a wire, that is my main bonding jumper, let's say, in a panel. So I can take my grounding electrode conductor, which typically has to connect to the XO, so it would be the XO bus, but I am permitted to connect it to the equipment grounding terminal bus only, provided that bonding jumper is sized properly. And so it's the same in a panel as it is in the transformer. So that grounding electrode conductor can actually connect to the equipment grounding terminal bus rather than the XO, because that is a wire type system bonding jumper and it was sized properly. Okay, so that's why in this picture here, people ask all the time, this is, why didn't you take this right here and connect it right here to the XO? Because this is a system bonding jumper was sized properly, I'm allowed to take it here to the bus, that type of thing. All right, Marlon, let me see if I can dissect your question here 2 hours into this. Okay, could we also take the half electrode to the panel ground bar? I think I just answered your question. Yes. As long in the transformer, yes, as long as this system bonding jumper is of the wire type or of the bus bar type and it is adequately or properly sized, then yes, just like it's shown here, you could take this over and connect it to this equipment bus right here. Perfectly acceptable, okay, because this is adequately sized. Is that answering your question? Thought I answered that question. I'm sorry. Let's see here. What's the last one here? H. Okay. H. And oh, by the way, the allowance that lets you do that, Marlon, is right here in 250.30A5, exception number 1. We'll go on and look at that since you brought it up. Let's see here. So let's go to 250.30. And look at that. Okay, so we know we're dealing with transformers. We're dealing with separately derived systems, right? And so let's go down into A5. So here's a grounded system. Okay, we have a grounded system. Let's go to A5. Okay, there you go. So grounding electrode conductor, and it says single separately derived system. Okay, so here's the exceptions. But let's look at the rule. It says a grounding electrode conductor for a single separately derived system, transformer in our case, okay, shall be sized in accordance with 250.66 for the derived ungrounded conductors. Okay, so we know we're using the secondary conductors to size it. Okay, so we're going to use 250.66. In that table, it has conductors on the left side. What do we use? We use those derived conductors. Okay, easy peasy. It says it shall be used to connect the grounded conductor, okay, of the derived system to the grounding electrode in accordance with 250.30A4 or as permitted in 250.68C1 through C2. Okay, so that connection, that grounding electrode conductor, is what's going from the EXO or from the system, okay? And in this case, it's saying it used to connect that grounded conductor all the way down to the electrode, whatever that may be, okay? So that's what's being used for. Now, that's what the grounding electrode conductor is when it comes to a transformer. Now, typically that would connect right to the grounded conductor, like it says, right? Straight from the grounded conductor to the electrode. That's what the code rule says. So that's why you have these extra lugs at the XO, because you may have a lug there, and it's 2 larger lugs and then 1 smaller lug, because that's where you take your GEC. However, you do get an exception to this. Okay? And remember, there's the same type of exception in a panel board applications that people lose sight of, and that's why my illustrations usually show the buses separated so that I can point that out. All right, so let's look at that exception that Marlon was talking about right here, exception number 1. It says, if the system bonding jumper specific to 250.30A1, so that's the single phase, a single separately derived system, right, is a wire or bus bar. A beautiful thing with the bus wire or bus bar, because that typically means that you size something, okay? So if it's a wire or a bus bar, maybe it's even a bus bar that's provided by the manufacturer where no sizing would be required because they providing it. But if it's a wire, we have to size it, so we got to know what we're doing, right, to size it. But assuming we do size it, and then again, that's why I like to show the separation in wires, because it forces you to have to size things. It says, where that's the case, it says, let's see, it should, hold on, let me read the whole thing because I broke it up. Except if the system bonding jumper specified in 250.30A1 is a wire or bus bar, it shall be permitted to connect the grounding electrode conductor to the equipment grounding terminal, that's what you ask, bar, or bus, if the equipment grounding terminal bar or bus is of sufficient size for the separately derived system. Okay, so there's an adequately sized. So the bus bar has enough terminations on it. It's typically provided, if it's provided by the manufacturer, it'll have openings. Other things to remember about a sufficient size, meaning that is the openings properly sized for the conductor that you're going to terminate onto it. Okay, that would bring into question if you have all these knockouts, for example, and then people do an extend-a-lug, but you do want to be careful from the manufacturer, because if the manufacturer says that the maximum size to be used on this bus bar is this size, That does not mean that you can always just keep adding extended lugs, or you can add bigger lugs and have it receive a bigger wire than necessary. Okay? Does not always mean that on those small little bus bars. Okay? Just be careful, especially if you buy these bus bar, these accessory packs. Okay? Doesn't always mean that. So just be careful. Read the information. Many of them will let you just buy an extender lug or an increased size lug and put it in there. But don't just assume anything for that, okay? But this does give you the ability to do exactly what Marlon's saying and not taking it to the XO, but I'll take it over to the equipment terminal bus, and that's why they usually give you a bus with multiple sets, multiple set screws on it, because you can do that, provided what? Provided that your system bonding jumper is a wire or bus bar and it's sized properly. We'll assume that it's sized properly, okay? For us, me and you, we'll assume you did size it properly. So that's what that means with the wire bus, okay? And that's what that exception means. Folks, that's why it's so important if you're in a fast track system that you do is stop and you go read those exceptions, most certainly, or read how the code reads. All right, lastly, H, we'll cover H and I'll spin the wheel. So here's that bus bar we're talking about right here. Again, not mounted on the ventilation holes, okay? All right, it says, where separate equipment grounding conductors and supply side bonding jumpers are installed, okay? In this case, it would be required. This one right here, you'll notice we got all this, okay, running up. Supply side, because of this flexible FMC, we have a supply side bonding jumper, so that's required. We got it. Up here, neutral bar is isolated. This one is connected to the enclosure. Why? Because the system bonding jumper is down here. Got it. So we got all that. It says now where that separately drives, where the separate equipment grounding conductor and supply side bonding jumper are installed, a terminal bar for all grounding and bonding connections shall be secured inside the transformer enclosure. No brainer. Says the terminal bar shall be bonded to the enclosure in accordance with 250.12 and shall not be installed on or over any vented portion of the enclosure. Should be a no-brainer, although I see a lot of pictures online where the bar is just right there over top of the vent holes. And you say, Paul, it's really not going to hurt anything. I'm just telling you what the code says. You do you, but that's what the code says. Okay, now, it says where a dry type transformer is equipped with a wire type connection, leads, okay, it says the grounding and bonding connections shall be permitted to be connected together using any of the methods in 250.8 and shall be bonded to the enclosure if of metal, okay? So sometimes in here you've got leads, or there may be, depending on the transformer, termination leads or whatnot. Again, the key takeaway here for most people in this transformer is usually you're going to have lugs. It's going to be a lug. It's going to be a lug bus. It's going to be mounted in the actual transformer. And that is the intimate. So interesting about a separately derived system, primary side does not come in contact with the secondary side except through the grounding and bonding. And that's okay. That's fine. It's still considered a separately derived system. Okay. All right, folks, as I sometimes do, it's a treat for those that actually do hang around because I can answer some questions. And if you hung around, that's why you never know when I'm going or when I'm staying. I've been gone for freaking 4 days, so hell, why not? So let's see. Marlon asked a question, says I have a 112.5 kVA 480-277 three-phase and install a 208 volt 120 panel board. I would say you can't, first of all, I'd say you can't install that panel board because that panel board, if it's 277, that panel board is only rated for 208 and 120 volts. So obviously can't use that panel board. But as far as the question goes, if I'm sizing primary, if I was doing, let's say a 480, okay, there's no point in having a 277 on the primary side. Why bring a neutral? It's not necessary because you're going to be deriving it from the secondary. So if you're bringing 480, ignore the 277, you're bringing 480 to the primary side, then you're going to size everything based on the kVA of the transformer, right? And you're typically, what you're going to do is, since you're going to be supplying a panel, it sounds like you're going to be supplying a 208 120, okay, which means it's going to have dual voltages. So again, your 240.21c is not going to come into play. So you're going to have some type of secondary protection. Okay, so you're going to do that probably in the first panel. If I'm going to follow the 10-foot rules, and you're going to put a panel right beside it, right? Okay, so assumes that your primary, whatever the transformer rating is, in this case, you said it was what was it, 112.5? So it's 112. So that is 112,500, okay, is what you're dealing with, transformer, right? So you do that, and we divide that by 480. Actually, in this case, you said it's three-phase, right? So it's 480 times 1.732, and that gives 831.36, right? So again, I like to use it all. A lot of people just use the 831. So then I'm going to take that 112,500, okay? And since it is three-phase, I'm going to divide that by 831.36, and that gives me 135.32. Don't forget, folks, if I didn't talk about it because we were talking very general, you still have to remember, if it's three-phase and you've got a kVA, okay, the voltage that you're going to be multiplying it by or dividing it into, that scenario, hold on here. My damn thing is frozen up. Shoot. Okay, well, okay, there it is. So anyway, sorry. So you want to make sure that you actually are doing 1.732 to the voltage in order to find out what your multipliers you're going to use. So then it would be whatever your kVA is divided into the 831.36, and that gives you 135.32 amps. I would take that 135.32 amps, and I would do that. I would take that 0.32 times 1.25, and that is 169.15. If it does not correspond, okay, so it's like, it's thinking, okay, well, does that correspond? Can I use the next size up? Well, remember, generally, you can go up to 250%. You don't have to go to 250%, right? But you still have to protect everything. So whatever the percentage is you use. So in this case, if I'm going to do that at 169.15 amps, then obviously an overcurrent device isn't going to correspond, so I can go to the next standard size. I'm not exceeding 250, and I'm not really going to the next standard size. I'm using the allowance to go up to 250%. I just don't have to, okay? So I'm going to do it that. So I would be at 169.15 amps, right? So then I would go to 240.6 to see what the overcurrent protection device would be for that, okay? And so I'm still not exceeding 250, okay? I only did the 125, but whatever I do for that is going to be mirror that when it comes to the conductors. Same concept, that type scenario. Does that make sense? All right. Hopefully I answered that question. Let's see what else is there. I had some other questions in here. Let's see. Anthony had some questions. What is he question? Okay, Anthony said something. What did he say? What do you do about the XO in the delta? Well, if you have a delta, you have an XO, then you do nothing with it, okay? If you're not deriving a neutral, okay? If you even have an XO in a pure delta scenario, okay? So do nothing with it. Is it a violation to bond it? Well, it depends to what. If you're going to the XO is doing nothing, because that's typically where, if there is an XO, that means there's a neutral point. Otherwise, you wouldn't need the XO. So it depends on the transformer. If it's a pure delta transformer that does not provide a neutral, or for some reason doesn't have the ability to provide a neutral, then going to it would generally be trying to create a neutral. And in that scenario, okay, you basically are trying to derive a neutral, but what do you derive? It's not going to be, what are you deriving it for? So you have to kind of know what your transformer is, what you're doing. So that's why I don't understand the question. The what if, the hypotheticals. If they do it, then they got the wrong type of transformer, unless they were trying to get a transformer that they need a neutral. And if it has an XO, it's assumed that it will be connected to the neutral point of that transformer, which would be to what? To be at a midpoint of one of the windings. So it sounds to me like that is a delta that can generate both a 120, a 240 volt application, or pure 240 volt delta. that type of thing. So again, it sounds like a transformer that may have multiple uses. And then Anthony says, so can you do this and serve a single piece of equipment with a secondary protection straight to the equipment, or do you still require to have a disconnecting means? All over the place with the question. When we talked about the disconnecting means on the primary side, that is only if you meet the 240.21c requirements and you have a single voltage output. Okay, single voltage input, single voltage output. That is when the primary protection can do both, protect the primary and the secondary. Only under that application. Okay, if I have a transformer with an XO, then it lends me to believe that it would be a transformer that is not a single voltage. That is a transformer that has the ability to have not just 240, but 120 because of XO termination. And of course, again, it's going to depend on the type of transformer. And maybe that transformer allows for multiple application. So again, I know what you're trying to do, and you're trying to be snippet at it. But, we don't do that on the morning show. Okay. Let's see what else. All right. I don't see any other. I guess I didn't miss any other questions. So anyway. All right. All right, folks. Take care. God bless. We'll catch you on the next episode of Coffee Hour. That'll be tomorrow. We'll have a different topic. Take care. God bless.